Okay, so chapter 32, electromagnetic waves. We begin with Maxwell's equations. Okay, so let's first write down Maxwell's equations. We can go ahead and number them here. The first equation that we took a look at was Gauss's law, which said that the electric flux through a closed surface let's leave that part blank for a second. Well, let's actually, we can put it in there. We'll examine that in a second. So the closed surface integral of E dot dA, which is the electric flux through the closed surface, is equal to the charge inside of that surface, which we can write down as a volume integral of a charge density divided by epsilon naught. So the charge inside the surface is simply integrate that volume charge density throughout that volume enclosed by the surface. We can do that because the surface on the left side, S, is a closed surface. It's a closed surface integral. And so if you have a closed surface, then inside of that surface, you have a volume. And this integral would be over the volume V. This is Gauss's law. So due to Gauss there. The second equation that we came across for Maxwell's equations was the closed surface integral of B dot dA. And this is a no-name equation, but some people call it Gauss's law for magnetic fields. And this flux through a closed surface is always zero. And this equation tells us that there are no magnetic monopoles in this universe. If there were magnetic monopoles, this equation would be equals something. It would be equals magnetic charge density, for example, maybe multiplied by mu zero. Okay, let's continue. The next equation that we saw was Ampere's law. Ampere's law was corrected by Maxwell, though. And so we'll leave Ampere's law last, because we'll need Maxwell's correction. And we'll go to Faraday's law. Faraday's law in integral form is a closed loop integral, E dot dl, on some contour or some path described by dl, which is tangent to the path. And this quantity here on the left, that path integral there, is the induced voltage, the EMF. So that's the script E. So we know induced voltage is equal to minus the change in magnetic flux. And I will use phi sub B for reasons I will explain later. So this is the flux for the vector field B, the magnetic field. Okay, that's Faraday's law. Nothing more to say about that. The final equation here is Ampere's law corrected by Maxwell. To start, Ampere's law is a closed loop integral of B dot dl, like the equation above, over some path C. And this was equal to mu zero, just some constant times the current that actually passes through the surface that is defined by, in fact, it's not even uniquely defined by, it's some current that passes through the surface with this boundary here, the path C. So remember, we could have a flat surface like this, right? That could be our surface, or we could have the same path and the surface could be like this, where it's kind of a plastic bag, right? Like a grocery bag surface. But you can see that the circular path there, those could be the same paths, right? And this was what we investigated when we looked at the issue of the capacitor's magnetic field, right? When a capacitor is charging up, we should be able to describe the magnetic field in between the plates. That was something that wasn't explained, in history until Maxwell came along. Everybody knew that there was a magnetic field in between the plates of a capacitor because you could measure it, right? You can just set up some instruments and measure that magnetic field. And but nobody really knew how to describe it. Okay, so there's one more term now, and that is the correction due to Maxwell. Maxwell says, well, to describe what happens in between the plates of a parallel plate capacitor, we should add in a term that has to do with the electric flux, and he called this term the displacement current. And displacement current, do you guys remember what that is? Displacement current. Displacement current is a real current if you have a dielectric. So if you stick a dielectric between the plates of a parallel plate capacitor, that material gets polarized, right? Quick little picture here. So here's a parallel plate capacitor. Here's a dielectric. And when you get that electric field between the two plates here, the electric field inside the parallel plate capacitor polarizes the charge. What you end up with is some positive charge here and some negative charge here. But the free charge is given by the sum of the charges on the plate plus the amount of kind of polarized charge due to that dielectric in the middle there. The technical way of writing it down is through the surface charge density. So you say the surface charge density at the plate minus the surface charge density at the surface of the dielectric is going to give you the free surface charge density. But in any case, when a capacitor is not fully charged, it has to charge up. And when it's charging up, there is a real current in that dielectric, right? More and more charge will become polarized as the capacitor becomes more charged. And as it becomes more and more polarized, that means charges have to separate, right? And so charges separating is the same as charges moving, and moving charges are current, right? So displacement current in a dielectric is a real thing, but displacement current in vacuum is not a real thing. We shouldn't use that word current to describe what happens in a vacuum. We should maybe use some other term. And that's exactly what we've done here is we've, instead of saying displacement current, we've said, oh, this is related to the time derivative of the electric flux. So we have magnetic flux giving rise to an electric field. So we must have changing electric flux giving rise to a magnetic field. I don't know if I said the first one right. So a changing magnetic flux gives rise to an electric field. Okay. So there's some symmetry there. There's some symmetry there in Maxwell's equations. Okay, let's fill in the gaps here. I mentioned that equation was due to Gauss. This one is due to Faraday. And this one is due to Ampere. And really there's a term in here due to Maxwell, right? We'll call that the Ampere-Maxwell law. Well, now that we're equipped with Maxwell's equations, what we can begin to do is convert these equations from integral equations into differential equations. And that sounds like a daunting task, and it is pretty involved mathematically. We need to be solid in our foundation of vector calculus, right? And the motivation for doing this is that we're going to make the equations somewhat more challenging to solve, but in doing so, we allow ourselves to solve for E and B in more situations. So the integral equations here require a large amount of symmetry in order to be used. So we require spherical, cylindrical, or planar symmetry, right? And that's a hindrance to our ability to describe E and B. So what we'd like to do is convert these equations to differential equations, and differential equations are local rather than global. So when you have derivatives, that's a local thing. When you have integrals, that requires knowledge over a large region, or over a region, not necessarily a large region. And so in converting these equations from integral equations to differential equations, we can actually expand the amount of electric and magnetic fields we can describe. Well, we can expand our solutions, so to speak, for E and B. We don't necessarily always need spherical symmetry or cylindrical symmetry or whatever. In fact, I remember when I was a graduate student, we were given a problem that actually had no symmetry, and of course, you can solve it using Maxwell's equations in differential form. And so that's the idea here. So we need to do a little bit of something on the side over here, and that something is going to be Stokes' theorem. Okay, we're not going to prove it. I leave that for your calculus teachers. Here we want to do physics, and so I'll present Stokes' theorem and maybe talk quickly about why that has to be true, and then maybe we can look at a little bit of physics as we go along to kind of see, oh, that kind of makes sense, right? So Stokes' theorem, what does it say? Well, the Stokes' theorem that you'll learn in your Calc 3 class is the following. So you have an integral along some path which is closed of some vector field f for field, and over some, like I said, over some path, and we'll just use dl to describe that path so that it's similar to what we're doing on the left side of the screen. That path is the boundary of something because it's closed. If you have a closed path, then that path is the boundary of some surface. If I have a circular path, then that could be the boundary of a disk, or it could be the boundary of some plastic bag, right? That happens to have a perfect circular opening. And so I will describe that as the boundary of some surface S. And this partial derivative sign, this D here, means boundary of S. So ds is the boundary of S, and S is some surface. On the right-hand side of Stokes' theorem, we have an integral over the surface which was bounded by the path described by dl. So we have a way of going from an integral on the boundary of something to an integral on that something rather than its boundary. And in order to make that change, notice that there are no derivatives acting on f, but there is, quote unquote, a derivative acting on the surface. We now want to flip the dependence there. We want to switch the derivative to the other term. So I want to, instead of integrating over the boundary, I want to integrate the derivative over the surface. And the way to get it right in this case is the curl of f. And the curl of f should be integrated over the surface. The curl of f is another vector. And so the integral on the right-hand side is the integral of a vector dot product with the surface. So kind of like the flux of the curl. That's, as a matter of fact, that's exactly what the right-hand side is. It's the flux of the curl of the vector field. However, notice that that integral on the right-hand side is not closed. I'll give you a second to think about why the integral on the right-hand side is not closed. So think about that for a second. Why can't the integral on the right-hand side be a closed integral? Anybody have any thoughts? Want to give any input? Okay, I'll go ahead and keep talking here, but hopefully you can think about that and figure that out on your own. Imagine we have a sphere. If this is a spherical shell, nothing inside, where is a closed path that I can say is the boundary of this surface? Well, for a closed sphere, there is no boundary. If I had half a sphere, again, empty on the inside, I could say this circle right here is the boundary. Okay. But if I take two halves and form a closed surface, I have no boundary. I have a closed surface. The closed surface is the boundary of a volume, right? If I had a full sphere that had a volume, the boundary of that volume would be the surface. The boundary of the surface doesn't exist. So the boundary of something is nothing. If I have something and I look at its boundary, that's fine. But then if I try to look at the boundary of the boundary, then it's not fine. It doesn't exist. Okay? So hopefully you can think about that and figure that out. We're going to erase this because we're definitely going to need the space. Now, with that in mind, that logic there, let me repeat the logic there for Stokes' theorem. I'm integrating a vector field on a closed path, which is the boundary of a surface. That is equivalent to integrating the derivative of that vector field on the surface itself. So again, we have in red here, we have no derivatives acting on F, but we have a derivative acting on S, which really just means the boundary of S. Here we have no derivative on S, but we have a derivative on F. That's how you remember Stokes' theorem. You have to get the boundary with no derivative and the inside of the boundary, in other words, in this case, the surface, with the derivative. Okay, so that's how you remember Stokes' theorem. Let's see another example of Stokes' theorem. This is a closed path integral given by the flux of the curl. What if we have a volume and we integrate over a volume? Or we have a closed surface and we integrate over a closed surface. If I integrate over a closed surface, a vector field F, like so, this would be by definition the flux of the vector field F. Well, a surface is a boundary of a volume. So if I define a closed surface, then I integrate over it. I can say, okay, I'm integrating over the boundary of the volume contained in that surface. Well, if I have a boundary with no derivative on the left-hand side, then on the right-hand side, I should have the volume itself, and I should have a derivative. In this case, it happens to be the divergence that is the correct choice for the derivative. All of this seems like I'm just throwing it at you, right? Like it's coming out of the blue. If you actually calculate the curl of f, you will see right away, term by term, everything matching up with the left-hand side. Same for this case here with the divergence. If you do f over an area, it will match up perfectly with the divergence of f over a volume. You just have to go and write it out yourself, and it will just fall right into your lap. I promise you, it's not difficult to check that this is a true statement. So proving it, though, maybe is a little bit more involved. You might have to go to the limit definitions for divergence and curl, right? And that's a little bit extra math, right? But let me give you the tools so that you can prove it for yourself, which you should do. Obviously, you should double check that what I'm saying here is correct. DL parameterizes a path, right? So DL is just a vector of dx, dy, dz. So it's dx in the x direction, dy in the y direction, and dz in the z direction, right? If I have a curve which is described by L, then if I take the differential of L, then it's going to give me the derivatives along each of those directions, x, y, z. So, for example, let's put it maybe in more concrete terms. If I have a vector r, then r is going to be given by x, y, and z. And then therefore dr would be given by dx, dy, dz, right? So it's simply a vector of differentials. That's all we mean when we say dl, right? We've seen that several times in class, so hopefully that matches up with what we've seen before. But we don't need to use r here. We're using L since we got to the chapter on magnetism, so I've just been following that notation there. So L. So dl vector is dx, dy, dz. How about dA? How about dA? For dA, take a look at a coordinate system. Here's the area A right here, or rather the area dA. And the vector dA is normal to the surface, right? Let's use black to kind of highlight the area a little bit more. So when I say dA there, I mean this area right here. Now, what direction is the z component? Silly. What direction is the dA vector here when the surface is in the xy plane? I already gave the answer away, but think about that for a second. If this is an xyz coordinate axis and the area is in the xy plane, then the area vector is normal to the xy plane, and therefore it is on the z-axis. So you can show, and let me write it in blue here, that the area differential, the x component is going to be dy dz, the y component is going to be dx dz, and the z component is going to be dx dy. Well, why is that the case? Why is it dy dz for the x component? Why is it d? Okay, well, let's look again at our example here. Here's the differential area element, right? It's in the XY plane. What is the area of this patch? I've called it dA, but what is the actual area? Well, here, the X length, the X side length of this square is dx. Well, it's actually a rectangle, but the side length there is dx. The side length here is dy, right? That's what we mean by a differential, right? Everything is differential in size. So dA has side lengths dx and dy when it's a surface just in the xy plane. Of course, if we have a more complicated surface, then we look at a small patch of area in that region, and it's the length of the side times the length of the side is the magnitude of that differential area vector. So it's not difficult to see that if we're working in Cartesian coordinates, then the x component is dy dz, the y component is dx dz, and the z component is dx dy. Okay, so I will copy that down again in black up above. So the area vector here, dA, which is normal to the surface, is dy dz, dx dz, and dx, dx dy. Excuse me, dx dz. Okay. Thank you. So we have now all of the tools we need to actually show that these two statements here are true. The second statement here is also part of Stokes' theorem, but some people call this the divergence theorem or Gauss's law or Gauss's divergence theorem. Although many different people were able to show this kind of independently, so it's a bit unfair to call it the Gauss theorem or whatever. But Stokes' theorem was the one who proved this in general for more cases than just three-dimensional vectors here like this. As a matter of fact, if you're in 2 dimensions or more than 3 dimensions, or I guess I should just say the simplest way. If you're not in 3 dimensions, the curl is not necessarily a well-defined operation. However, there are ways of generalizing what we mean by the curl of a function, some vector function or some higher dimensional object, the curl of a matrix or something like that. And some of those objects are actually important in quantum mechanics. For example, angular momentum is a vector in classical physics, right? So you guys study angular momentum, right? Torque. Those are vectors. But in quantum mechanics, angular momentum is not a vector, it's a matrix. And so, there may be some situations where you need to generalize, for example, what you mean by divergence or curl when you run into objects like that. So they're higher dimensional objects. Okay. So we have the 2 Stokes theorem cases that we need here for you're right, Sarah. It should be dx dy there. Fix that up real quick. So it should be dx dy there on the last term, the z component of the area vector. Okay, so what else do we need here? Let's remind ourselves, well, actually, let's do that when we need it. So let's go ahead and make some room for ourselves. And we're really going to just be operating on a single sheet today for the most part until we do like some examples. Because otherwise we're going to have to keep writing Maxwell's equations like over and over and over again. That's going to get really time consuming. So I kind of did it this way for the other class and it still was kind of a long whoops. Still was kind of long, so move this up. But we were able to do some examples at the end, though. So okay, so the flux integral here, we can match it with the Stokes theorem over here at the bottom. Notice that we're integrating over a closed surface, so we cannot use this formula here because the right-hand side of this formula is not a closed surface integral, okay? So there is only one way ever to apply Stokes' theorem. You never have a choice. It's one way, that's it. You cannot choose. So when we apply Stokes' theorem, it says, change the surface integral of E dot dA into the divergence of E integrated over the volume. So integrate the divergence of E over the volume. And now we have volume integrals on both sides of the equation. Of course, it is standard practice then to put both terms under the same integral, and if the integral equals 0 for those for the sum of those things, then what's on the inside must be 0 for some arbitrary integration measure. So since the volume that we're integrating over is arbitrary, then obviously the thing on the inside must be 0. Then you can move the row back to the other side, blah, blah, blah. Essentially, let me just put it in layman's terms. Just cancel the integration. You just cancel the integration. That's what we do. Okay. We don't have to be so mathematically precise. So we come across our first example of Maxwell's equations written in differential form. Why didn't we start with this when we introduced it to the class for the first time? Well, because nobody knows how to solve partial differential equations, right? I mean, in this class. If you do, then you are one of the lucky who has been able to get through a lot of math before taking this class, which actually, I mean, I recommend. More math is better when you take physics, for sure, because you don't have to focus on the math as much. You can focus more on the physical understanding. So we now delete what is on the inside and we delete the equation up here, and now we take this equation and we raise it up as equation 1. Okay, and we begin working on equation 2, and I invite you to just go through this yourselves. I have to move the equations around and clean up the board and stuff. If you know what you're doing, go ahead and work on that and get ahead, right? Apply Stokes' theorem and see what you get, and then maybe you can compare to what I get when I get there. So in order to apply Stokes' theorem for this equation here, it's exactly the same as equation 1. So we have the surface integral. It is a closed surface in this case. So we only have one option here, and it is to use this version of Stokes' theorem, not this version up top, because again, on the right-hand side of this version here, we do not have a closed surface integral. Okay. Back up, let's clean it up. Apply Stokes' theorem. In the interest of keeping things, maybe a little bit less boring, I'll go ahead and switch colors here on this one. So on the left-hand side, we have the integral of the divergence of B over some volume element now. But on the right-hand side, nothing has changed. We just have 0 on the right-hand side, right? So nothing really to do there. So since the integral of the divergence of B is 0, then the divergence of B must be 0. So we can go ahead and switch it back, or rather cancel the integration, so to speak. Divergence of B is equal to 0. And so I will delete, kind of do it slower in case some of you are still writing. So now we changed it to this, integral of the divergence over a volume is 0. Right? And then now we have the divergence of B must be 0 as a consequence of that. Okay, how about equation 3, Faraday's law? Right, what do we do for Faraday's law? Well, this time we have an integral over some line element, some path, some contour, some curve, right? And it's a closed path. So this is like this. I cannot use this expression there. I can only use the top version. Okay, so let's go ahead and rewrite it then. So again, maybe I'll swap the color. Keep things interesting here. The curve here, I can change from integration over a curve to integration of the boundary of a surface. So the first thing I'll do is I'll change C to ds. So it is the boundary of some surface. So C equals ds. So I can write now the integral of over the surface S, which is an open surface, the curl of E dot product with dA. And that should be equal to minus the time derivative of the magnetic flux. So let's write the derivative part. And then we come over here and we add to our toolbox. What do we mean by the flux of some vector field F? The flux of some vector field F is a surface integral of that vector field F on those elements of the surface dA. So dot product of F with that surface element dA, integrate over the whole surface. So that's what we mean by flux of a vector field. So if we plug that definition in, we have integral over a surface of B, it's the magnetic flux, B dot dA. That. We have to do a little bit more work here. So this side of the equation remains unchanged. Curl of E over the surface S. And now on the right-hand side, I would like to switch the order of integration and differentiation. This is where things get a little bit tricky mathematically. If my integral that I'm taking the derivative of with respect to time does not depend on x, y, or z, then I have a total time derivative and there's no issue. However, if I move the time derivative inside of the integral, then it is acting on the magnetic field, and the magnetic field can depend on both x, y, and z, and time t. The functionality, so to speak, of x, y, and z is that of coordinates. They are not describing the position of a particle, kinematically. They are simply coordinates in space, time that we're dealing with here. So we have a space, we have a vector field on that space. X, y, and z are simply telling us where we are in space. So when I bring the derivative inside of the integral, I better switch from a total time derivative to a partial derivative with respect to time to ensure that I understand t is playing the same role as the coordinates x, y, and z. I wouldn't want to make the mistake of having a magnetic field which depends on, let's say, x, y, and z, and when I take the derivative d by dt, I see an x and I say, oh, x dx by dt is the velocity. No, that's not what's happening here. We're talking about the time rate of change of magnetic flux. The time rate of change of magnetic flux means derivative with respect to time, not with respect to, so we're not taking a derivative of x, y, and z with respect to time because x, y, and z are coordinates. They do not depend on time at all. They're completely independent of time. They simply tell us where we are in space. So when I switch the order of integration here, when I say integral of b dot dA over the surface S, if I switch the integral outside of the derivative, I must change this derivative to a partial derivative with respect to time. And of course, the area vector here does not depend on time. In the strictest sense, this is a differential area element. It only coarse grains, so to speak. It's a patch of space. It only depends on x, y, and z coordinates. It does not depend on time. We have seen some problems where we've stretched a stretchy ring and changed the surface that we've used to calculate the electric flux. Well, there's a more rigorous procedure than what we've done kind of so far with Faraday's law in that sense. Although, I mean, the integral equation for Faraday's law is still valid there. That's totally okay to have the area change, and it's just not something that can happen here when we bring the derivative inside of the integral. That area element there does not change. We always treat the magnetic field as something that changes with respect to time. The area element here does not depend on time. Okay, so now what? Well, again, we have integration over the surface S on both sides. So we cancel, and we're left with the curl of the electric field. Plus the time rate of change of the magnetic field is equal to 0. Okay, and I've simply added the time derivative to the other side. I think it just makes it a little bit easier to remember it once you see the other equations. Okay, so let's clean this up. We're done with that integral equation. And now we have a partial differential equation in x, y, z, and t. Right? Notice that the first two equations are three-dimensional differential equations where time is playing the role of just strictly a parameter. It's not necessarily a coordinate in equations 1 and 2. There's no time derivative that shows up in equations 1 and 2. In equation 3, the derivative with respect to time shows up in the differential equation. So this equation is four-dimensional in a coordinate sense, and time is not playing the role of a parameter. Time is playing the role of a coordinate. In equations 1 and 2, time is simply a parameter, a bystander, basically. You just ignore time. All the time functions just cross over the derivative. They're not affected by the derivative at all. In equation 3, not the case. Magnetic field depends on time, and there's a derivative with respect to that. Therefore, the curl of E is going to be a function of time according to the derivative of the magnetic field with respect to time. However, of course, if the electric field depends on time, then the derivatives that you see there in that equation, the curl of E, none of those derivatives act on time. And so again, when you go to compute the curl of E, you see that the time functions just pull out of the derivative. The derivative does not act on them. Okay, time for the final equation. On the left-hand side of this equation, we have again a contour integral or a path integral or a line integral of the magnetic field, and it is a closed path, and therefore we use the first option here on the right-hand side. We use this option, not this option, when we change the integration. So again, let's do it. Maybe let's switch colors again here. We're on purple now. So the integral over the path is the same as the integral over the surface, provided we have a closed path. The curl of that vector field, which is B, dot product with dA. And that must be equal to mu0 times I, but again, we need to do a little aside. We need to talk about what we mean by current. Do that in black over here. Current is given as an amount of charge which flows through a cross section of a surface. In other words, just any surface. In mathematical language, it would just be any surface. So we can write that as an integral on some surface of a current density, and that current density has different values potentially throughout that surface. So we can write the current as the integral over the surface of the current density dot product with that area vector. In other words, the flux of the current density through some arbitrary surface there, but not a closed surface. Okay, if we have that, then we can write it in here. So integral over a surface of J dot dA go back to purple, plus, again, epsilon naught, mu naught. And then we've got to fill in for the flux again. This time it's the electric flux. So again, in general, flux is a surface integral of the vector field which is E in this case, dot product with dA. And notice again, we have all of the same integration on every term in this equation, right? And so we can get rid of all of these integrations. The standard mathematical procedure for that is to put everything on one side and under the same integral, and then claim that since the surface that you're integrating over is an arbitrary surface, then the only way for that integral to be equal to 0 is for everything on the inside of the integral to be equal to 0. But just to make it simple, we can just say, all right, cancel the integration on all sides. Right? So cancel the integration. So we have the curl of B. I will now subtract. I forgot a term in the equation. I forgot the time derivative here on the last term. I want to subtract this term to the other side as well. And remember that when I bring the time derivative into the surface integral, I must switch from a total time derivative into a partial derivative with respect to time, because time, again, is playing the role of a coordinate here, not a parameter. And the other coordinates, of course, x, y, and z, do not depend on time. So there's no sense in having a total time derivative. That in essence, that's kind of meaningless because time is a parameter, or sorry, time is a coordinate, not a parameter. Derivatives with respect to coordinates are partial derivatives. Total derivatives are derivatives with respect to parameters. That's maybe a distinction you did not learn in your calculus class, but it is definitely something of utmost importance here at this stage. So something maybe to remember. When you're taking a total derivative, that is with respect to a parameter within your equations. Okay. If you're taking a partial derivative, then that means you're taking a derivative with respect to a coordinate. Now, in many cases, you can treat parameters as coordinates and coordinates as parameters, but just for the kind of concreteness of it here, we're changing the total derivative with respect to time to a partial derivative because t is playing the role of a coordinate. So let's subtract that over to the other side. So it's the partial derivative of the electric field with respect to time. And of course, I forgot my constants here, so there should be an epsilon naught and a mu naught multiplying here. So epsilon naught, mu naught. And this should be equal to mu 0 J. J is the current density. Okay, so we have 4 equations. Or rather, we have 4 vector equations. We actually have how many equations here? We have an equation for every component of E and B. So question for you guys. E has 3 components and B has 3 components. We have 6 components. Therefore, we have 6 unknowns. So here I see 4 equations. How are we going to determine E and B? How is that possible? We have 6 unknowns and only 4 equations. Anybody have any ideas? Does anybody have any ideas? You see one chat here. I'm still thinking, okay. It's a very interesting question, right? We're saying that we have 4 Maxwell equations and this completely determines the electric and magnetic field. But a closer look says we have 6 unknowns and only 4 equations. Math it out to solve for the other unknowns. Yeah, more equations. I mean, yeah, more equations. Concatenate the equations together. But that, okay, so if you really want to talk about something along those lines, you would have like a linearly dependent equation if you tried to sum 2 equations or something like that. So the unknowns would have to be dependent on each other. Well, let's do one thing. One thing that is kind of actually maybe a little bit exciting. You haven't seen before. Well, I know you probably haven't seen this before, but I'm talking about something we've seen before but haven't seen before. And that's conservation of charge. How do we know charge is conserved? We know that because there's a conservation equation hidden in Maxwell's equations. So we actually have conservation of charge hidden in here. The way that we get that is by taking the divergence of equation 4. Okay? So if I take the divergence of equation 4, that equation is completely independent of the other 4 equations that we have here. If I take the divergence of it, that's derivatives, right? Derivatives are independent of the thing that you're taking the derivative of, right? So the divergence of the curl of B minus epsilon naught mu naught. By the way, when I say the word independent, I mean independent in the sense that it's not the sum of any of the other equations, right? So I know obviously like you take the derivative of something, of course it depends on the something you're taking the derivative of, but I mean it's not some sort of combination of 1, 2, 3, and 4. Okay, so divergence of equation 4. I can switch the order of derivatives here and take the divergence of E inside the derivative with respect to time. The reason I can do that is because the del operator there is derivatives of x, y, and z, right? It's just derivatives. So if E is a real vector field, I can switch the order of the derivatives, no problem. Because if E is real, that means it's not infinity anywhere and it's not discontinuous anywhere, right? So as long as it's not discontinuous somewhere or infinity somewhere, you can always swap the order of the derivatives. And then the last term here is mu 0 divergence of J. Okay. So divergence of the curl of the magnetic field, what does it equal? The time rate of change, the time derivative of the divergence of E, what does it equal? Divergence of J, what does it equal? One of these terms in this equation is 0. You guys tell me which one is 0. one of the terms in this equation is 0. Divergence of curl is 0. Anybody else have any other input? That's only one person, so think about it. Placing my bet on the middle term. I like that there's a little bit of disagreement. Munfeng says because the second equation. Interesting. I like the thought process. Keep thinking. Keep thinking. I want to hear from some more people. So people who haven't said anything, let's hear some input. You can discuss in the chat too if you want to ask somebody why they thought that, or if you want to change your answer, feel free to change your answer. Don't just go with the popular answer though, right? Actually try to think about the reasoning. Isn't the dot product a constant? So taking the derivative of a constant would be 0. The dot product is not necessarily a constant. The dot product takes two vectors and maps them to a scalar, right? So constant and scalar are not the same thing. Although you may have the impression that scalars are constants because of how they're talked about in like your first semester physics class, right? You're used to doing dot products and you get some number, right? But the answer you get from a dot product of two vectors which depend on time is going to be some scalar which depends on time, right? Okay, so I think that's enough discussion there. So I think you guys all are engaged and thinking about it, so that's good. Let's go ahead and discuss it now kind of as a class here. So anytime you take the divergence of the curl of something, you always get 0. Let's try to understand why that's the case really quick by looking at maybe one component. Okay, so if I have the divergence of, well, let's, yeah. So this is always zero by definition. Let's try to understand why. So the curl of a vector field F, what does the x component look like? Well, the x component is going to be x hat times some stuff, right? What is that stuff going to be? Well, you have to form a matrix, right? You have to form a matrix, so the curl of F is given as the determinant of a matrix with x hat, y hat, z hat on the top row, and then the second row is derivative with respect to x, derivative with respect to y, derivative with respect to z. This is shorthand notation for the partial derivative. So d by dx is by definition dx, like that. So it's like a partial d with a subscript x. That's x derivative there. Okay. And then you have fx, fy, and fz. This is just all by definition here. We haven't done anything but definition of the curl here. So I take the first, definition of cross product, my bad. So the cross product says take the first vector and put it in the second row. Take the second vector, put it in the third row. And in the top row, put your coordinates, right? So x, y, z, hat. And then take the determinant of that matrix. Let's look at the x component. So let me just go ahead and show here. So this is the x component. So it's going to be x hat. Oh, I already have it written down over here, right? So we can do it in red. So x hat, open up a parentheses, right? And now I have y derivative on the z component minus the z derivative on the y component, right? So y derivative on the z component minus z derivative on the y component. Okay, that's the x component of just the curl. So this is just the curl. What would the divergence be? Well, the divergence would be a dot product of del and this vector here, del curl f. Sorry, del cross f. So I would take an x derivative of this thing, right? It has x hat, so it's going to be d by dx times this component right here. So d by dx acts on this thing here. So it's going to be d by dx, d by dy of fz minus d by dx, d by dz of fy. So divergence of the curl of f be equal to, there's no x hat anymore because the divergence of this vector is going to be a scalar, not a constant, but a scalar. In this case, a scalar and a constant, and that constant is 0. But what does it equal here? It's going to be two derivatives on fz, one with respect to x, one with respect to y, minus two derivatives on the y component, okay? And of course, we're going to have 6 terms, right? We're going to have 6 terms. So the y hat component, is going to be d by dx on fy minus d by dy on fx. And then we're going to take a y derivative, right? Sorry, I think I said that wrong. It should be d by dx of fz and d by dz of fx, and then take a y derivative. So we're going to have mixing of y and z derivatives and x and y derivatives. And then we're going to have mixing of z derivatives, and it's going to be like d by dz of d by dx of the y component, right? So all different combinations are going to be added in from the divergence, and they will all cancel. Let me know if you can see that that's what's going to happen. So in the chat, or give me a thumbs up or something. So you're going to have all combinations of second derivatives there. There are 6 possible combinations. You're going to have all 6 of those combinations, and they'll all perfectly cancel to give you 0. You're going to have an xy, you're going to have an xz, you're going to have a yz, and you're going to have an xz. And then you're going to have, each of those are going to be acting on fy, x, and fz, and they're all going to cancel perfectly. So write it out by hand for yourself to complete the picture in your notes, to show that the divergence of the curl is always 0. Okay. Just real quick, just for the sake of completeness here, just let's write down the y hat component. It should be minus y hat. It's going to be dfz by dx minus dfx by dz. And then you're going to end up taking a y derivative of this thing. So it's going to be minus dfz dy dx plus df x over dy dz. And let's see, can we already see cancellation? Yes, we can. We can see cancellation of the z derivative. Look here, the z derivative. Sorry, the z component. This z component and this z component are going to cancel. You see that? And then when you do the z component, these other two will cancel. Okay, so that's all I'll say about that. So the divergence of the curl is 0. So we get 0 here for this term. I should have done this. So we have 0 there. Minus epsilon naught mu naught. What is the divergence of E? What is the divergence of E? Look at Maxwell's equations. What's the divergence of E? You want to know what the divergence of something is, or you want to know what the electric field or magnetic field something is? You always look at Maxwell's equations. Divergence of E is in this equation and this equation only. It's rho over epsilon naught. So we have d by dt of rho over epsilon naught. And that equals mu naught divergence of J. Great. Look, we have a nice little cancellation. Epsilon naught and epsilon naught cancel. What are we left with? Mu 0 and mu 0 cancel. and we're left with conservation of charge. This is a continuity equation. d rho dt plus divergence of J. Notice there's a minus sign. Notice this minus sign right here. So I can add it to the other side. Time derivative of the charge density plus the divergence of the current density equals 0. Right? So if the charge density changes with time, then there must be some sort of current, or if there's some sort of current coming in, then there must be, I guess I should be really specific. I should say if there's a net current. So if the charge density is changing with time, then there must be some sort of net current flowing outward or inward. And if there's a net current flowing inward or outward, then there must be a changing density. There must be a density that changes with time. Okay, so the divergence of the current density means how much of it is flowing out or how much of it is flowing in, right? That's what divergence means. Flow out or flow in. Flow outward is positive, flow inward is negative, right? So if I have the divergence of the current density is positive, that means I have positive flow of charge outward. Positive flow of charge outward means positive charge leaving the charge density. So if I have positive flow of charge outward, then the rate of change of my current density is negative. It's becoming less positive. If positive charge flows out, the density of charge becomes less positive. In other words, d rho by dt is a negative number. Okay? So we have conservation of charge now. This is a continuity equation that applies to more than just conservation of charge. This is kind of in general terms a continuity equation. Anything that's conserved will obey an equation like this. For example, another example is you can have let's say you have a situation like this where we have some sort of situation where there's a current coming in, but that current also leaves. In that case, the total divergence is 0. So the divergence of J is 0 in this case. If we have J coming in and J going out, right? Divergence is 0. Because J is a constant vector, right? So technically there could be more J leaving than there is coming in. Let's make it so that it's the same. Then there's no change in the charge density. This is what, this continuity equation is kind of what explains what's going on with the capacitor, right? So you have the surface of one of the plates of the capacitor is becoming charged as the charge density comes in. So there's a divergence of the charge density. And so that charge comes in as a current and then stays there. It stays on the plate because it comes in as a current, but it doesn't leave as a current, right? It comes in, but it never goes out. And on the other plate, there's a current going out. And so the charge density on that plate is opposite to what it is on the other plate. And so you can look at a capacitor as a total system where there's just a charge, there's a current density just kind of going in and going out. but you have polarization of charge there. So probably a better way of looking at it is what goes on one plate and then look at what goes on in the other plate. Of course, the two charges have to be the same, because if I treat the two plates as one system, in other words, if I put them in a box, I have current going in and I have current going out, and the two are equal. And so the net charge on that system remains constant. It remains zero because it was zero before. Okay, that's conservation of charge. That's one more equation, right? That's one more equation. So we're still missing one apparently, huh? We have 4 equations, plus now we have charge conservation. That's 5 equations. You might be thinking, the Lorentz force. Nope, sorry. That equation tells you how particles move in the electric and magnetic fields, not how electric and magnetic fields. It's not a constraint on the electric and magnetic fields. So I'll leave the last bit there as an open question for you guys to investigate on your own. So we have 4 Maxwell's equations. We just got conservation of charge. That's 5 equations, but we have 6 unknowns. So how are we supposed to solve for E and B? How are we supposed to solve for E and B? There's one more topic of importance that we should cover from chapter 32 before we move on and do examples. And let me remind myself of what that was again. Right. Oh no, we didn't even derive the wave equation yet. Okay, so that's the next thing we'll do, and then there's one more topic. So there's 2 more topics. Okay, so I'd like to start from a clean slate here. So I'm going to grab these equations and I'm just going to pull them down with me here. And we only need these equations. We will need another vector identity. Let me see if I remember it. I only saw it one time and wrote it down one time for last class. I didn't do it from memory. I looked it up. Let me see if I can do it. So I need the curl of the curl of a vector field. Now you might be thinking, oh, wait a minute, the divergence of the curl is 0. This is probably going to be 0 too. Don't make that mistake. That is not true. And then you might say, hold on a second. Any vector cross itself is 0. So A cross A, is 0. So this is going to be 0, right? Because this is the same as del cross F, right? No, don't make that mistake. The cross product is not associative. If I have A, B, C, and I multiply B and C, that's the same as A and B first, and then multiply by C. That's the associative property, right? The cross product is not like that. So the curl of, I should use vectors probably, A cross B first and then cross C is not necessarily equal to A cross B cross C. Okay. In general, this is not the case. And furthermore, when you have derivatives involved, you have to be extra careful, because when derivatives act on functions, they change the function, right? And so here we have derivatives acting on f, which is a vector function, right? It's going to change it up a little bit, although it's true that this is kind of still acting like a cross product with the del operator, and then you're going to do the del operator cross product again. Some weird things can happen when you take derivatives. You have to be extra careful. Okay, so what is it then? Well, let's get rid of the junk here. This is equal to the, let's see if I remember this. So one of the terms is the Laplacian on F, and the other term is, I can't remember. The curl of the gradient, maybe? No, that's not it. Let me look it up. So there's stuff even I can't remember. So curl of a vector. Let's see here. Oh, it was, I did think of this, but I wasn't sure. So it's the gradient of the divergence. There we go. The gradient of the divergence. Yeah, it involves del, exactly. Okay, so it's the gradient of the divergence of f. The Laplacian right here, which is the del squared thing, this is like del dot del acting on a function, or acting on a vector field. You can think of del dot del as simply second derivatives added together. So you're taking second derivatives and you're adding them up and letting that operator act on some vector f. Okay. So this is just a vector identity that you can prove. You can just go through the motions of computing the curl of something and then isolate the equations component by component, and then you can clearly see something like, oh, it's an x component, but it has y and z derivatives, so that's going to be like the curl, right? Or you can see actually, so that would be like on the left side of the equation because you're doing curl of curl. So it's second derivatives which are mixed on the left hand side, and then on the right hand side you have only derivatives with respect to x, right? And then you have derivatives like plus y derivatives on x components plus z derivatives on x components from the third term here on the right hand side. I guess the second term on the right hand side. So you just break it down component by component and you just go through the computation just manually and write it all out. And you'll see that this is another true statement here. So now that we have this, what should we do? Well, you're probably guessing already, we need to take the curl of one of these equations, right? So let's take the curl of the most difficult equation here. Let's take the curl of b. Let's take the curl of, the curl of b. Let's start with the most difficult one first and see, oh wait, it's not that difficult. So the curl of b minus epsilon naught mu naught times the, let's go ahead and pull the time derivative out. The curl of e. And look at that. What's the curl of e? We already know what the curl of e is. That should be equal to mu naught times the curl of j. Right? Mu naught times the curl of j. Okay. If we have the curl of the curl, then we can write that as, according to our identity on the right-hand side, we can write that as the gradient of the divergence of B minus the Laplacian on on B. Okay, and then minus the rest, right? So we've used the identity now. What is there left to do? Does anybody see anything special here that we can change? What can we change here? What simplifications can we make here? What simplifications can we make here? What can we do? There's two things I see. I see two things. Maybe you see more than two things. Maybe you guys see more than two things. So what can we do here? I mean, I see one term that's zero for sure. Which term is zero? You guys spot it? Look at those terms. Which term is going to be zero? Which term is going to be zero? I'm sure you guys are just still writing. You're only halfway through the equation. I'm asking all these questions. Oh, still nobody, huh? Anybody see anything interesting in this final expression here that we have? Like any term zero? I see one term that's zero. Does anybody notice? When Feng comes in to save the day, he thinks the first term is zero. Does anybody agree with that? Anybody disagree with that? Anybody see any other terms that we can change in this equation? Maybe look at Maxwell's equations. Maybe they give us a hint. David says change del cross E, the curl of E, into minus dB dt. I like it. I like it. That's coming from equation 3. I'm surprised nobody wants to put their answers in chat here. So let's go ahead and look at some stuff here. So the divergence of B is always zero according to equation 2. The curl of E is minus dB dt, right? Let's fill it in. So we have 0 minus the Laplacian or del squared on B minus mu 0 epsilon naught. Whoops. Epsilon naught mu 0 second derivative with respect to time on the magnetic field. Okay, that's kind of interesting. So we have two derivatives with respect to x, y, and z, and why not two derivatives with respect to time? Space and time are on equal footing here. All right, space and time are on equal footing. Another indication that t is a coordinate here, not a parameter. And that's integral to understanding special relativity, that t is a coordinate and it transforms like a coordinate, which tells you that not everyone measures time the same way that you do. The measurement of time depends on motion. Okay, so what's left is this oh yeah, no, we're fine. Is this curl of J term. The curl of J. Let's do the same thing for the other equation, the curl of E. Let's take the curl of E, and what do we get? If we take the curl of E, we get something similar, like gradient of the divergence of E. You get like the gradient of... So let's take the curl of equation 3 now. So the curl of E plus d by dt of the curl of B, right, equals 0. Well, the curl of E is the gradient of the divergence of E. Okay. I know what the divergence of E is. Do you know what the divergence of E is? Minus, in fact, minus the Laplacian del squared on E right, plus d by dt of the curl of B. Curl of B, let's replace the curl of B. The curl of B is epsilon naught mu naught dE dt plus mu naught J. Look at that. So replaced the curl of B from the fourth equation, from the Ampere-Maxwell equation. And the divergence of E, what is it, guys? Tell me what it is. What's the divergence of E? What's the divergence of E? It's not 0. Check Maxwell's equations. Check Maxwell's equations. Always look at Maxwell's equations. Always look at Maxwell's equations. Elaine, though, I will point out that we will look at a case here in a second where rho and J are 0 to simplify everything, because everything's a little bit complicated and messy right now. We will simplify things, and we'll see that wave equation. So rho over epsilon naught, I like it, David. That's equation 1, right? Maxwell's first equation, the Gauss's law equation. So we have the gradient of rho over epsilon naught minus del squared E plus, and then all this stuff here. So epsilon naught mu 0, second derivative with respect to E plus, and now this is where things get crazy right here. It's like, oh, we have a derivative on J now. That's where things get really messed up, because you can't really have a derivative on J with respect to, I guess actually it's not so bad. It's not so bad. Derivatives on J are kind of a slight difficulty, in the sense that if you look at point charges, it's difficult to define what you mean by the current density. If you have a point charge that's moving, it requires the introduction of this function in quotation marks called the Dirac delta function, which is not really a function, it's a distribution. And so derivatives of that thing can get kind of nasty. But derivatives with respect to time is okay, because you can track the position of a charge using the coordinates. You don't need to use the time. Okay, so let's group some terms now. So I like this term. I like this term and I like this term. Why do I like those terms? Well, they both have second derivatives with respect to x, y, z, and t. So let's write it as epsilon naught mu naught d squared e by dt squared minus del squared on e, and then plus this nasty stuff here. So 1 over epsilon naught gradient of rho plus mu naught time derivative of j with respect to t. Okay, things are looking kind of grim here for us, but not so bad actually. Okay, what do we do now? So we have two new equations. They're not really all that new, but they look kind of new here. Let's go ahead and highlight them. This equation here, and we have this equation here. Okay, let's get rid of the rest of the clutter. Now, neither of these equations address the question that I mentioned before, where I said, okay, we have 5 equations now, and we have 6 unknowns. Neither of these equations will address that issue. Okay, so I haven't answered that question for you, so you should still go and take a look. That whole idea about needing, we really need 6 equations, right? So these 2 equations do not answer that question. Okay, so what question do these equations answer? Well, these equations are equations involving fields which satisfy something like a wave equation, but not exactly. So let's go ahead and rearrange this equation here. I want to take this stuff here. I want to change this plus sign right here to an equal sign. And I'll put a minus sign on this term and a minus sign on this term. And this term here is gone. So I subtracted those 2 terms to the other side. That's what I did. And look at this term right here. I made a sign error on this term. I'm not really sure what happened there, but there's definitely a sign error. What did I do? Well, that's correct. Oh yeah, I put in an extra minus sign. So when I take the curl of, when I took the curl of E there, I forgot to include that there should be a minus sign because I have to move dB by dt to the other side. So that should be plus right there. So let's fix it. So this one right here should be plus. Let me highlight that for you guys. So this one right here should be plus. Okay, so I've moved all of the sources to the right-hand side. And on the left-hand side, I have wave equation material. Because what is the wave equation? The wave equation in one dimension is 1 over velocity of the wave squared, du, two derivatives with respect to time, so du dt squared, on u. U is just some function that describes a wave. For example, on a string. Maybe you saw this equation in the first semester, maybe not. But there it is. At minus two derivatives on this function u with respect to x. And this would be a one-dimensional wave equation, or rather 2 dimensions if you want to say time is a dimension here. Usually for Newtonian physics, time is not a dimension, it's a parameter. It's not a coordinate, it's a parameter. And so you wouldn't consider it a dimension, so to speak. But in this situation up here, we actually have time as a coordinate, not a parameter. And what that means is that the 2 equations above are 4-dimensional equations. They're equations of space-time, not space, with time as a parameter, but space-time. The reason we use that word space-time is because time and space are on equal footing. They're both coordinates. Okay. This equation equals 0. So if we want to make these equations look like a wave equation, we have to get rid of all of the sources. We have to say, let's look at these equations in vacuum. In vacuum, we don't have charges or currents, right? So the charge density is 0, and the current density is 0. And you might be thinking, oh, wait a minute. If there's no charge and there's no charge density, there's nothing, right? Those are meaningless equations. Not true. What Maxwell's equations are telling us is that there are electric and magnetic fields in vacuum, and we'll see, we're about to show, that those are waves. So they travel and carry energy in vacuum. Okay, so that's the profound result here. That's the prediction by Maxwell for the existence of radio waves, light, X-rays, gamma rays, infrared, right? So here's the thing, set rho and j equal to 0 in these equations. We have epsilon naught mu naught from the first equation. The first equation. The second equation, we'll do that one in a second. B, second derivative of b with respect to time, minus del squared on b, and that should be equal to 0. We're setting j equal to 0. This is a wave equation. Then for the second equation, we have epsilon naught mu naught, second derivative on E with respect to t. Look at this. Electric and magnetic fields being treated the same in vacuum, right? Identical. You can just naturally switch between the two of them. If you've solved the equation for one of them, you've obviously solved it for the other one as well, right? Okay. So there we go. We have 2 vector wave equations. So the x component is a solution to the wave equation. The y component is a solution to the wave equation. The z component is a solution to the wave equation. All 3 components individually satisfy a wave equation. Now, those of you who have studied the wave equation, which I'm sure is very few of you, but maybe some of you have seen it before, you may remember that we're kind of in another pickle, so to speak, here. Because the wave equation can be solved in general, and the general solution is way too general to be useful. So what do I mean by that? Take this one-dimensional wave equation right here. The solution to this equation is any function u, which is a function, any function, literally any function, of the form x minus vt. So this function here, which could literally be anything. So I'll write down so if u equals the magnitude of x minus vt, that's a solution. If u equals e to the minus x minus vt times the magnitude x minus vt raised to the power x minus vt, this is also a solution to the wave equation, barring any discontinuities here in this function. If there's discontinuities in that function, which I think there might be, then it wouldn't solve the wave equation at that point. But you get the idea, right? Here's another solution. This is probably one of the more useful solutions. Some amplitude a times sine of, some constant here. Maybe let's call it, I don't know what to call it. Let's say b times x minus vt. And this is maybe one of the more useful solutions because it looks like a wave. That's why. Let's just be honest here. The wave equation has so many solutions which are like not waves. So we're kind of in another pickle here where E and B are just kind of very arbitrary in what they are. But at least we have a general solution now for E and B in vacuum. So we've literally solved all of E and M in a vacuum simply by writing these two equations down. There is nothing left to do in vacuum other than perhaps the next topic, which is how energy is carried in the fields. So we've seen in the past for capacitors and for coils of wire that they carry energy in their fields, right? So the energy density for the electric field is 1/2 epsilon naught E squared, right? And energy density means density per unit volume. And then there's also magnetic energy, which is 1/2 mu naught B squared, right? So there you go. Those are your energy densities. That clues us in to what we're going to do next. So let me go ahead and take this, and I'll give you time to write this down in a second. I'm going to take this and move this over here. I'm going to delete this. Okay. And I just want to now look at two terms. I want to compare this with this. Solve for V. You go ahead and do it yourself. Solve for V. Write your answer in the chat. Solve for V. 1/v squared has to be equal to epsilon naught mu naught. What's V going to be? Let me get some water while you guys solve. What do we get in here? What do we get for V here? This should be like a one-liner. Shouldn't take too long here. Just rearrange for V. Just rearrange for V here. Should be a one-liner. Wait, what? No. We're comparing two terms here. We're comparing this term with this term. Look, this is what we're solving. We're solving for V from this right here. Notice on the time derivative piece here, the velocity, 1 over the velocity squared appears. Here's the time derivative, so this must be 1 over the velocity squared. Ooh, okay, good. Alberto, Alex, Yuan, good. Okay, perfect. We get 1 over the square root of epsilon naught mu naught. Calculate that value. Epsilon naught is 8.85. I think 4 is the next digit, times 10 to the minus 12 farads per meter. For mu naught, it's 4 pi times 10 to the minus 7 Tesla meter per amp. Calculate that value. What do we get? Calculate that value. What do we get there? More significant figures. More significant figures. More significant figures. This has 4 significant figures. This has an infinite number of significant figures. How many significant figures should your answer have? There we go. 4 significant figures. There we go. There we go. What are the units? What are the units? How can we be so sure? Epsilon naught times mu naught is farad Tesla meter over meter ampere. Is Tesla times farad over an amp? Is that really going to end up giving us what, seconds squared over meters squared? Is that really going to give us seconds squared over meters squared? Where do we get farads from? Farad is a coulomb per volt. Coulomb per volt. Tesla is, what is Tesla? Tesla would probably, the best way to write a Tesla is Newton per coulomb meter per second. So that would be an amp meter. So Newton per amp meter. Can we combine these units and get seconds squared per meter squared, which is what we would need? The answer better be yes, okay, but let's not spend too much time on it because it's got to be true, right? You're all getting the speed of light, and that is exactly it. And that is exactly what Maxwell recognized right away. 2.998 times 10 to the 8 meters per second. That's the speed of light that was known at the time. Or rather, that's not the value that they actually knew at that time, but that is what he did. He calculated that value, recognized that it was very close to what they had measured for the speed of light in the most recent time, during Maxwell's time that they measured the speed of light, right? So he instantly recognized that, right? He's a trained physicist. He knows, he sees, wow, okay, this is the speed of light. There's something extremely important going on here. So it tells us that the speed that the electric and magnetic field move with is the speed of light. So that should right away tell you that light is a consequence of the electromagnetic field. The two fields should be considered as one field at this point, the electromagnetic field. All right, how is energy carried? How is energy carried throughout the field? Well, let me just pull up a nice little image here. I'm actually going to take this and move it. I'm actually going to take it over here. And then we're going to bring this in like this. And we can think of a wave front, meaning there's some wave moving in space. We call it a plane wave. And the plane wave is described by the solution I kind of hinted at earlier. It says that for E, you have some maximum value, E0 times sine of 2 pi over the wavelength, and then it's x minus vt. But v here, remember, v is c, the speed of light. Okay. Another way of writing this, which is completely equivalent, is to say that it's E0 sine of kx minus omega t. And you can figure out what k and omega are from there, right? And I think you guys already know omega, it's like 2 pi times the frequency. And k is just that quantity that you see right there, 2 pi over lambda. So we can write that. K is 2 pi over lambda. That's called the wave number. And omega is the angular frequency, 2 pi f. And omega times k is, of course, the speed, which is the same as, I made a mistake here. It's omega divided by k is the speed, which is the same as the frequency times the wavelength. Okay. Now, how much energy is carried in this thing? Well, if E and B satisfy the same equation, then it makes perfect sense that B would have a similar solution. B would be something like B0 sine kx minus omega t, right? But there's a little bit of a thing that we should do here. We should multiply both sides of this equation by c, the speed of light. And the reason for doing that is so that what we do next, which is recognize that the electric field and the magnetic field are related, by this expression here, that the maximum electric field has to be equal to C times the max magnetic field. And the reason for that has to do with the following. Well, really, where that comes from is maybe a little bit beyond what we're supposed to cover in this class, and it has to do with special relativity. But I think I can give you a really good picture of why that has to be the case, or at least make you question why that has to be the case, so that you'll actually go and figure it out yourself. And here is the picture I want to show you. Suppose I have a wire like so. And in that wire, I have current. And the current is flowing in this direction. Outside of that wire, I have a charge. Let's just take it to be positive. And that positive charge is moving with a velocity v. So I have a current here, and I have a charge moving with a velocity v. What's the direction of the magnetic field here at this positive charge? Well, right-hand rule. Get your right hands up. Good test practice. Put your thumb in the direction of the current. So put your thumb pointing to the right. Curl your fingers. Your fingertips better be coming out of the page. Right here, right? The magnetic field is circulating around the wire like so. Right? This magnetic field is curling around the wire. In other words, the curl of this magnetic field is not zero. Just to tie everything into what we've already done with the curl and divergence and stuff. The divergence of this magnetic field certainly is zero, right? I mean, it's only curling, it's not diverging. Okay, well, there's a magnetic field there. That means there's a force on that particle, right? What's that force going to be given by? Well, it's going to be given by F equals QV cross B, right? And what's the direction of that force going to be? Well, fingers in the direction of V, and then I got to curl them. I got to curl them out of the board, right? So the force is down. The force here is down on this charge, right? Well, hold on a second. If I go into the frame of the charge and I move, I am the charge. I move with the charge. I'm the charge. I'm moving with this velocity v as seen by some stationary observer in the lab. I'm moving along with this charge, and I set my velocity equal to the drift velocity of the charges in the wire. Remember, what is current? Current is a bunch of charges, and all of these charges have random motion, but they have a velocity which is special. It's called the drift velocity, and that is the velocity due to the electric field inside of that wire. So if I match my velocity with the drift velocity of the charges in the wire, I see no current. Think about that for a second. If I have this positive charge move with the same velocity as the charges in the wire, it will see no current in the wire. It will measure zero current in the wire. Giving you some time to think about that.
Are you saying there will be no current or there will be no measurable?
What's the difference? Everything has to be measurable, right? So if the positive charge measures the current in the wire, it will measure zero. Therefore, it cannot feel the effects. It cannot feel the effects of those moving charges. It does not see a magnetic field. It does not see a magnetic field. And therefore, it does not experience a magnetic force. So this Lorentz force here would be 0 for a charge moving with v equals the drift velocity. Think about that. And therefore, that positive charge would only experience electrical forces if that wire, let's say, were charged, if it were actually a charged wire with a current. If I had that positive charge move with a velocity equal to the drift velocity, it wouldn't see the current, but it would still see that there were charges on that wire, an excess amount of charge on that wire, and it would still experience an electrical force. Where's my mouse at? There it is, okay. So B can be made equal to 0. A question for you guys to investigate. The answer lies in special relativity. So the answer is contained in special relativity. Okay. And since I can go into a frame of reference, I can move, I can change my velocity so that I don't see a current, this must be true. This statement right here must be true. There must be a relationship in some frame of reference where I can write down something having to do with E and B, because if I can't do that, then I could never express something like this or something like this and say that's the total energy in the system, right? If I co-move with the current, then I don't see a magnetic field. So therefore, all of the energy in that particular system should be given in terms of E squared. And E, in certain situations, I should be able to make E go away, but I can't make B go away. So it starts to get really interesting once you get into special relativity. Okay, so that brings us to what I want to cover, the last thing I want to cover here. And the last thing I want to cover here is energy transmission. So something called the Poynting vector. One more quick point about what I said 30 seconds ago, that sometimes I can make the magnetic field go to 0. Sometimes I can make the electric field go to 0. There are conditions when I cannot do that. For example, if I say there's an ambient uniform magnetic field everywhere in space, so if everywhere in space there's like a magnetic field here, and it's not due to some current of some kind, then how would I move to make that magnetic field zero? The answer is, well, I wouldn't really have a way of doing that, right? Actually, there may even be a way to do it actually in this case, but you get the idea. Certainly, there are some cases, like for example, in quantum mechanics, where you cannot do it because the magnetic field gives rise to what's called hyperfine splitting of the energy levels inside atoms. And so it's impossible to get rid of that splitting of the energy levels. It's a real physical measurable thing, no matter what reference frame you have, because there's a delta in the energy associated with that hyperfine splitting. And so that difference between those energies could shrink or get larger based on the motion, but the actual splitting itself cannot go away. And therefore, it's impossible to get rid of the field which is responsible for the splitting. Hopefully, you guys follow the logic on that. Maybe that was too advanced, but yeah. So there are some situations where you cannot make the field go away because there are physical consequences of the field being non-zero that wouldn't be there if the field was zero. Okay, pointing vector. Pointing vector. Pointing vector, we use the letter S. The pointing vector, simply put, is 1 over mu 0 E cross B. Pointing vector is E cross B. Get your right hands out, look at the figure, put your fingers in the direction of E, curl them in the direction of B, right? Right hand rule. What's the direction of S? Use the right hand rule to find the direction of S. Get my right hand here. It's like, which way do I curl my fingers? This way. Okay. Maybe that's enough time for you to figure it out. I get that S is in the same direction as C here. Is that what you got? So S is a vector which points in the direction of the velocity of the wave, labeled C here in this figure. And the electric and magnetic fields are oscillating back and forth between, positive and negative, positive and negative. And the magnitude of the pointing vector, in the case of a plane wave like this, is 1 over mu 0, magnitude of E, magnitude of B, times the sine of the angle between those two, which of course is 1 in this situation, because the angle between E and B is always 90 degrees. E and B are always perpendicular. Now, E and B will increase and decrease, and eventually they will both become 0 at the same time. And when that happens, then the pointing vector is 0, but, right, the average pointing vector is maybe a nice indication of how much energy is kind of always being transferred through vacuum. Doesn't necessarily have to be through vacuum, but whenever we see mu 0, epsilon 0, we're thinking vacuum. If we don't want to do vacuum, we always add kappa right? Or something along those lines. Um, the average Poynting vector is EB over 2 mu 0. The reason it's over 2 is because when E and B switch directions, the Poynting vector is still pointing in the same direction. And so the Poynting vector looks, the Poynting vector is kind of doing something like this. So, okay, here's what we need. E, we can write as, again, some maximum value of the electric field times sine kx minus omega t, right? This solves the wave equation. This is one possible solution of the wave equation. Okay, fine. How about B? Well, B we can write as B0 sine kx minus omega t. Okay, good. Well, if I take these and I plug them in here, what do I have? Well, I have that the Poynting vector, oh, sorry, whoops. I should plug them in here. If I take the average of the Poynting vector, sorry, I meant the, oh, whoops, wow, there's a lot of mistakes here. I meant the average of the vector magnitude. Sorry about that. So maybe the one way to write that would be S average here, like that. So if I plug those in for E and B magnitude, I get a magnitude, I get a sine squared, right? So if I average over sine squared, I get a 1/2, right? For the average of sine squared. So that's where the factor of 2 is coming from. And then, of course, we had the relationship that E0 must be equal to C times B. And so we can actually reproduce what we saw before. S average is, let's put it as, let's substitute B for E. So E squared over 2 mu 0 C, and mu 0 C is going to end up giving us what does it give again? Mu 0 times C. C is what is it again? V squared. So 1 over square root of mu 0 epsilon naught. Wait, so did I make a mistake? Did I make another mistake here? EB. Make another mistake here. Double check here. Wait, am I just substituting in wrong here? If I substitute in for B is E0 over C. Sorry, yeah, these should also be E0s. E0 and B0. This should be an E0 squared. So this is, I'm getting a weird extra factor in here. No, oh no, this is correct. This is correct here. This is correct. Oh, I don't need to do this. Oh, okay, I see, I see. This can be converted. So I can actually, okay, so mu zero times c, 1 over mu zero times c, I can write as 1 over mu zero, 1 over square root of epsilon naught mu zero. And if I do that, then I can I can cancel a square root, so to speak, here. So I have 1 over square root of mu zero over epsilon naught, and then this thing will flip up and multiply square root of epsilon naught over mu zero, like this. And then this right here, I can then write as epsilon naught times c, and then I can rewrite the average magnitude of the Poynting vector here as 1 over 2 c epsilon naught e squared. Okay, there we go. That's what I was looking for there. Okay, and so this tells us what the Poynting vector really is here. Okay, this tells us what the Poynting vector really is here. So notice it's not energy density, right? This is not energy density. Energy density looks like this, 1/2 epsilon 0 e squared, right? So to get energy from this, you should integrate over the volume, right? So you should multiply top and bottom by V, and I mean volume here. So like, so if I wanted the total energy in the electric field, it'd be 1/2 epsilon naught E squared times the volume V, because it's density. So and really I probably should write it as an integral, to be honest. But in a simple case, maybe you can integrate with respect to V. If I wanted to write the Poynting vector related to some sort of energy, the way it has to be done is you have to write it in terms of an intensity. Okay, so let's see, maybe the best way to do this is to go here, pull this up. Oh, whoops, wrong thing. There we go. Okay. So from this figure here, we can see that at time dt, the volume between the stationary plane and the wavefront contains an amount of electromagnetic energy, du equals uac dt. Now, what is this? Okay, look at what we've written here. Look at what we've written here. So we're saying that energy density contained in the electric field is 1/2 epsilon naught E squared. And there's a volume here. And the volume, dV here, is A C dt, right? So if the volume is AC dt, then I can write the total electric energy stored in that volume as 1/2 E naught E squared A C dt. Does everybody follow me on that? I probably should actually write this as du. Sorry, this should be a du because I have dt on the right hand side. Okay, So hopefully you guys are with me. Let me see. There's a chat here. So okay, yeah. So this is the amount of energy that's stored in that little piece of volume there due to the electric field. So what we can do now is we can understand the meaning of the Poynting vector by grouping the stuff that we have here, which is this part here and the C, and then moving all the other stuff to the other side. So we take this and we say, okay, we have du by dt, and we have 1 over the area. This is equal to 1/2 epsilon naught c times e squared, right? So just move those terms to the other side, move the dt over. So we have the derivative of the energy with respect to time, the rate of change of the energy. That's power, right? That's power. And that power over area, that's intensity, right? That's intensity. So this right here is S average. And then we now recognize this as power over area, which is intensity. So the Poynting vector tells you about the intensity of the radiation, of the electromagnetic wave. Tells you about the intensity of the electromagnetic wave. Do bear in mind that this is in vacuum. We have mu0 and epsilon 0 floating around. We don't have any dielectric constants or magnetic materials here that we're looking at. One final piece that we'll do before we finally end things off is the actual integral expression for the power. So I should be able to calculate the power by looking at how much flux there is from the Poynting vector. So the flux through a closed surface is how much the flux of the Poynting vector through a closed surface is how much energy escapes the surface per unit time. So the integral of the Poynting vector over some area, this is flux now, over some surface. So flux of Poynting vector through surface tells us how much energy escapes. Or, well, we could think of it maybe as energy that leaves the system, right? It tells us how much energy leaves the system as radiation. And when we say radiation here, we specifically mean electromagnetic waves escaping to infinity. How much leave that surface. So if I put stuff in a ball, right, and I see that there's electromagnetic waves coming out of that ball, then I know that I have electromagnetic waves escaping out to infinity. That's radiation. That's one definition of radiation anyways. So it's energy flow per unit area per unit time through a cross-sectional area perpendicular to the direction of propagation. Let me say that one more time. The Poynting vector is the energy flow per unit area per unit time through a cross-sectional area perpendicular to the propagation direction. Okay, let's end things there. I've been talking for way too long. I need to give you guys some problems at this point, right? I'm sure you guys are bored of this stuff. I know it's interesting, but like, you're probably bored anyways. So let's do some examples from chapters 27, 28, and 29. But before we do that, I'll allow you guys to ask me any questions, right? So if there's any questions about what we covered here, it is important stuff. You should understand it for next semester. Maybe, this Thursday when we don't have class because of Veterans Day, maybe you want to read chapter 32 and kind of do some of the examples in that chapter. Although that might take away a little bit from your actual studying. But sometimes it's good to parse your studying out, right? And rather than study for 8 hours, you study for a couple hours and then do something else, right? So maybe to stay on topic, to stay kind of close to physics, you could take a look at chapter 32 a little bit. Or maybe after the test, before you want to start working on the next chapter, maybe you take a look at some chapter 32 stuff. And even take a look at chapter 32 after the semester ends before you get into chapter 33, which is what you'll start with next semester. And you guys will have Peter Widman for 223. So I believe he's using Young and Friedman. So yeah. So you should all be good to go in that respect. So okay, so I'm gonna go ahead and clean this up. So we'll do a new sheet here, sort of the top. Now we're gonna do examples. We're going to do simple examples, right? We're going to do simple examples from the back of the book. So they're not examples from the chapters, but they're going to be back of the book questions, fairly straightforward questions, the kind of questions that you might see on a test, okay? Which physics book is your favorite? You mean to teach from? I actually really like Young and Friedman, but I think I'm going to switch books next semester. Because I'm going to completely change how I teach the class that I'm going to be teaching. I think I'm going to use Eric Majour's book, but I really like the Young and Friedman, and actually, thinking about it, I think I can do what I want to do if I were using the Friedman book too, but I've been doing a lot of research on how to actually increase learning gains for students. And there's so much evidence supporting the techniques certain techniques. So I want to actually adapt, not adapt, but adopt just a full adoption of best practices for peer instruction for next semester. And the textbook that I want to use is by Eric Majour. I think it's called Physics Principles and Practices, something like that. And the presentation of the material throughout that textbook is organized slightly differently than standard textbooks. And what's crazy about it is actually, it seems like something that's so obvious to do. One of the differences is in standard textbooks, you're often taught about force, and you do all of these difficult problems from kinematics and dynamics, and then you say in the next chapter you do work, right? You complicate things even more by saying, look, if we do work on things, it's integral of a force times displacement, and oh, you're adding energy to this thing, this quantity, this thing that you're doing, this force over a distance is adding what we call energy to this, to the particle. And so, okay, so we've defined what energy is, and then you say, but if the force is conservative, then we can define a potential energy, and then you say, okay, so energy is conserved. So we can do all of those hard problems that we just spent 3 or 4 or 5 or even 6 chapters sometimes doing the hard way. Now we're saying, they're all easy problems. Look, energy is conserved. And then write the answer in like 2 or 3 lines, right? And then the same thing happens with momentum after that. So once you cover energy, then you do momentum. And then all of a sudden you have, as a consequence of Newton's third law, you have conservation of momentum. And then again, look at these collision problems, these complex interactions, these crazy forces, which we can't even write down necessarily, but we can plot them and say, area under the curve is the impulse and all this. And then you have conservation of momentum. And again, you can do complex problems very simply using algebra. So the idea behind the textbook is to completely flip that and put force and things after you do conservation laws. So you cover conservation laws first as a consequence of experimental evidence. So you do experiments, and those experiments tell you energy is conserved, and they tell you momentum is conserved. And as a consequence of those conservation laws, you can deduce the dynamics from that. So, and what's funny is, like, you guys learn all this stuff about force and velocity and things like this, and those concepts are not useful in higher level physics. It's very difficult to define the velocity of a charged particle in practice, in the quantum mechanical sense, which is what we know, electrons and protons and things to be. So doing things from conservation principles first seems like a really good idea, because you start with algebra rather than starting with like calculus and stuff. Of course, you have to cover kinematics first, though. You can't do anything without kinematics. Professor, I remember you saying that you would be releasing a giant problem set for chapters 27 through 29, but I don't see that on Mastering Physics as of yet. That'll go up tonight. That will go up tonight. If I put that up before today, then no one would have showed up, and they all would have just been working on that assignment, and they would have just forgotten about me. Okay, anyways, let's go ahead and get into some questions now. So we'll get into some questions here. So let me not pick exactly the same questions that I chose for the last class. That way they can come and watch the video and they'll get some little bit extra. Okay, so let's take a look at this one here, 29.3. Yeah, we can do a review session. Yes, I'll send an email out about that as well. The magnetic flux through a coil is, and by the way, as we go through these example problems, I want you guys to focus on the reasoning, not getting the formula and getting the answer, but focus on the reasoning, the problem solving strategy that goes into the problem. Okay, I think that'll often, if you just kind of recall a formula and you just go and plug and chug, that's when you kind of make mistakes. So let's try to focus on the reasoning as we go through these examples. And I'll put you guys in groups and you guys can discuss that and try to, you know, like convince each other of your method or whatever. If you disagree, just really focus on the reasoning today. Okay. So the magnetic flux through a coil is given, which question am I typing? There we go. Is given by, and then I'll leave some space where A and B are constants. What are the units of A and B? If the induced EMF is 0 at t 0, 500 seconds, how is A related to B? And if the EMF at t equals 0 is minus 1.60 volts, what is the EMF at t equals 0.250 seconds? So a few parts here for this question, and the magnetic flux here, phi b, is a function of time. It is, oh wow, there's a typo actually here in the e-text. It actually gives alpha t minus beta t cubed, but then it says A and B are constants. So it should be AT minus beta t cubed. They probably do that on purpose so they can sell you on the next edition, right? It's like, oh, we made a typo on page 1023. Now we can publish the next edition. Oh, whoops, I messed up again. It should be a lowercase b. Okay, so this question here, let me see. Let me approximate the amount of time it would take to do this question. Part A, 30 seconds. Part B, maybe a minute. Part C, maybe 2 minutes. Okay, so let's give 5 minutes for this question, okay? Let's give 5 minutes. Should I put you guys in groups or do you want to work on this one solo first? For next semester, what I'll be doing is a method called peer instruction. I'll be asking students questions, not necessarily of this nature here, like a back of the book problem, but I'll ask the students to think of their answers by individually first and vote on answers, and I'll collect the distribution on that answer. And then I'll ask the students to find somebody nearby who has a different answer than they do and discuss and try and convince each other, focusing on, making a proper argument as to why their answer is correct, or maybe they discover that their answer is incorrect because of something the person they discuss it with says. And it's been shown that peer instruction nearly doubles, doubles to triples learning gains for students. So I'm trying to really get best practices in my classroom. So your high school debate class could have come in handy. Often debate in the context of law is not very applicable in science, because there's a lot of times where you're trying to convince somebody of an opinion, right? Not an actual fact, not a scientific fact. So probably not. I would argue that you should not rely on techniques from a debate class, but you should just have sound logical arguments. I suppose if you took a class on debate, you might learn how to construct solid arguments, but yeah. Oh, you were joking. Well, it's kind of hard to tell if somebody's joking when they just type a message in chat, right? So I blame you. Yeah, so 5 minutes, guys, 5 minutes. Yes, everything is funny if you type. Yes, you just have to type LOL. Oh yeah, that's a good one too. Yeah, XD. Oh, now we're all sad because one student is attacking another student in chat. No bullying in this classroom. Okay, let's focus on the problem. Okay, let's focus on the problem. David as well. Let's focus on the problem. Okay, it's been 5 minutes since the last time I said 5 minutes. So we do want to make sure that we're able to kind of keep time, right, on certain questions. So use that as kind of an indicator to you, like, oh, okay, wasn't able to finish part C, so maybe I'm a little bit slower, right? So you have to time manage a little bit on an exam, right? Um, so answer to part A here, we'll just go over quickly. I think it's very straightforward. The units of A have to be flux, which is Tesla meters squared. These are SI units, by the way. Tesla meter squared per second, because it's multiplied by T. The units of the left side have to be equal to the units of the right side. The SI units for B are going to be Tesla meter squared per seconds cubed. Right? So is this what you guys were getting? You can just put a yes in the chat or something. For part B, if the induced EMF is 0 at t equals half a second, how is A related to B? If the induced EMF, well, induced EMF is minus the rate of change of the magnetic flux, right? Well, minus d phi by dt is minus a minus 3b t squared, right? And we're saying that the induced EMF is 0, so that means this thing equals 0 when t is 0.500 seconds. I think I maybe wrote that a little bit strange. Let's actually do this. So what I'll do is I'll clean that up. I'll put that in there. I'll put it in there like this, and I'll just put it in parentheses and square it. That's basically 1/2, right? 1/2 of a second, so it's a quarter. So what we really have here is A equals minus 3/4 B. Okay, A is minus 3/4 B. So to answer part C, if the EMF at t equals 0 is minus 1.60 volts, what is the EMF at t equals a quarter of a second? Well, at t equals 0, we have minus 1.6 volts. So minus d phi b dt evaluated at t equals 0 is equal to minus a minus 3b t squared equals minus a, right? So minus a equals minus 1.60 volts, which means A is 1.60 volts. And now we can see that, remind me why EMF isn't minus A plus. Oh, it is. You're right. Yeah, I forgot the minus sign there. Sorry about that. So it is plus. Good catch. So that means now that we have A is 1.60 volts, which, by the way, that tells us right away that Tesla meter squared per second is actually a volt, right? So we can actually say that's volts there. And then we can even say that this is volts per second squared, right? Okay, so now that we know what A is, we also know what B is. So let's just get that real quick. 1.6 over 4 is, what is that going to be? 0.4, right? And then multiply by 3 is 1.2. So B equals 1.20 volts. Oh, wait. Just this one, I guess, and this one. So what is the EMF at t equals 0.250 seconds? Well, EMF again is minus d phi b dt, which is equal to minus a plus 3bt squared. And we want to evaluate this when t is a quarter. So this is going to be minus 1.60 volts plus 3 times 1.20 volts times a quarter squared, which is 1/16. We just crunch that on the calculator real quick. 1.6 plus 3 times 1.2 divided by 16. We end up with 1.825. Questions about that one? Or should we go to the next one? Could you back up to how did 3bt squared become positive? Yes. This is phi. So the derivative of phi is, well, sorry, minus the derivative of phi is minus a plus 3bt squared. So we have to include the minus sign here because EMF is equal to negative d phi b by dt. To answer the next question, Professor, I got B equals 4/3 A. Yes, B does equal 4/3 A. I plugged A in for B on accident. And now I'm realizing that. I should be more careful. So it's good you guys are paying attention. You know, this is a good test, whether you guys are paying attention. So 1.60 volts should have been plugged in on this side here. So it should have been 4/3 A is equal to B. So B would have been equal to, so 2.1, you guys were saying, 2.133. So that's probably a repeating 3, right? So, and that would be volts per second squared. Okay. So we have B. Oops. Okay. That means for this part right here, we don't have 1.20. Everything else is correct, but we need to plug in 2.133 bar. So let me go over here and fix it up. And we end up with 2 for our answer. All right, are we all in agreement now? So we're not in agreement. Do I have another mistake? Wait a minute, did I change the wrong thing? I just changed the equation I had already in Wolfram Alpha. Maybe I accidentally times 16. Oh yeah, it is. I actually read the number incorrectly. It was minus 1.2 and I called it 2. Yeah, I guess I'm really tired, guys. Like I actually barely slept last night. So it should have been minus 1.2 volts. There we go. Okay. Well, it's good that you guys are paying attention. So that means you're at, you don't always get this, you don't always get students correcting you. It's a good sign that people are paying attention. So, all right. Are we good on that example now? So there's no more mistakes? Give me a yes if we're good on that one. What was that? My Calc 2 professor said, when the math stops working, it's time to go home. Yeah. When the math stops working, right? Okay, so we'll go ahead and go to the next one. So that was an example of Faraday's law, right? Which is chapter 29. So let's go ahead and let's do an example for maybe chapter 28 now, right? So sources of magnetic field. Go to the questions here. Let's look for another kind of similar difficulty question, not too hard, not too simple. I did that one with the last class. Maybe we'll look at okay, I think this is simple but requires thought. Okay, so let's do this one. It also comes with a bit of a figure here, which is nice. Copy this over. Two long, straight, parallel wires, 10 centimeters apart, carry equal current, equal 4.0 amp current in the same direction. Find the magnitude and direction of the magnetic field at A, point P, midpoint. Let's just simplify this part. I think it's straightforward. So A at the midpoint, B 25 centimeters to the right of okay, 25 centimeters to the right of the current on the right side, okay? And then for part C, 20 centimeters above the midpoint. This one's a little bit more involved, so this one probably wouldn't be asked. Certainly I wouldn't ask you to do all of these parts on the test, right? But I could ask you to do one of these on the test, right? I could ask you calculate B, right? That could be a question on the test, or calculate C even, or calculate A, right? So those would be valid test questions, but not all of this together. So let's go ahead. We're already actually over time here. Let's go ahead and put you guys into groups. If you have to go, you have to go. But let's put you guys in groups. I will do random groups, 2 to 3 participants. So one of you will only have 2. Let's see who it is here. That should be fine. Let's go ahead and open up the rooms. Go ahead and get into your rooms. Focus on, again, focus on the reasoning, right? Don't just remember the formula and go from there. Focus on the reasoning to really get the most out of these problems. Go ahead and join your rooms.
There are.
Okay.
I just
Here,
want you guys to understand the question. That's it.
Yeah, we got it.
Okay.
Yeah.
That's the
Just want to check to see if we understand the question.
Yeah, we're just trying to figure out magnetic field, this specific point, right?
I recommend that to get a little bit extra practice, think about Ampere's law. Rather than going and grabbing the formula, recall, right, that you have Ampere's law to figure out the magnetic field, just to get a little bit extra. Okay, I'm gonna go to the next one. Just checking to see if you guys understand the question.
I think so. For the first, for part A, I'm thinking it's 0, since it's kind of in the middle or midpoint. For B,
Probably think a little bit, be able to explain why part A is 0 a little bit better than that. To really hone in on your understanding of what's being asked, right? Does that make sense what I'm saying?
well, it's just that they carry equal current. So that doesn't that kind of cancel?
What are we asking for though? We're not asking for current.
Midpoint. I need to think about this one.
Okay. Yep, I'm just trying to give you like some tips about how to get more out of your study problem. So always try to like think about the reasoning and kind of justify your answers a little bit more. I think you kind of have an idea what's going on, obviously, but be able to really articulate that. So that way you can kind of increase your own understanding of the problem. Alex, did you have any questions?
None right now, or actually just for like part B and C, like how would we like do those?
Well, for part A, if you know how to do part A, you know how to do parts B and C. if you know the answer for part A, then you will not know the answers for parts B and C. Does that make sense?
Yeah, makes sense.
That's why I was telling Tatiana, be able to justify your answer a little bit more. So as a general tip, right, I would say here in this problem, we have currents and we're being asked about magnetic fields. So we've got to, at some point, use Ampere's law, right?
Yeah.
So use Ampere's law to figure out the magnetic field due to those current carrying wires. And don't rely on something memorized, right? So like Tatiana, I think what you were saying is that you just know that it's going to be 0 in the middle because it's going to be the same magnetic field for each of the wires, right? And they're going to be in opposite directions, but you should recall, okay, I got to use Ampere's law here and that kind of stuff, right? And so now that I've done the right hand rule, now it makes sense why they're in opposite directions and all that. Okay, so I'll let you guys work on that. Okay, I'm gonna wait maybe, I wanna say like 2 more minutes before I actually visit the groups again. And just for those who are watching the recording, let me go ahead and give you a little bit extra here. So what I was telling Tatiana there a second ago was, it's kind of something important, is that you should focus more on the reasoning as to why it's 0. It seemed like there was an understanding that in the middle there, let me not use an X, but at this point here, that the field is going to be 0 because the magnetic field due to the current, due to this one here, is going to be down. I should be a little bit more precise there. It's going to be down this way from this one. Oh, excuse me, I don't even have the correct direction here. It's upward. I should be using the right hand rule. So thumb coming out, fingers are curling up at the midpoint. And then on this other one, on this other current carrying wire, do the same thing. Magnetic field is going to be going down. You should be able to justify that answer a little bit better to really understand what's going on in these problems, because if you cut corners a lot on problems, then you'll get asked a question where you don't know how to cut corners on it. And instead of investing time into getting the actual problem solving techniques down and the actual understanding, you've committed to memorizing how to cut the corner, how to get to the answer quick, right? And so you've missed out on that understanding. That understanding could have been applied to a question you've never seen before, but that corner cutting method, or that kind of memorizing, kind of a short subset of what to do, got you an answer to a question you kind of already knew, but it can't get you to an answer for a question you've never seen before. So in essence, the magnetic field around a current carrying wire, curls around that wire according to the right hand rule. And at fixed radius, that magnetic field is constant in magnitude, and it's along the theta hat direction, so it's curling around the wire. And the magnetic field is given by mu 0 I, the magnitude, mu 0 I over 2 pi r, and if you want to put the direction in there, it's theta hat. But if you just remember this value, this answer for the magnetic field, then you've missed out on an opportunity to apply Ampere's law. Ampere's law says take a closed loop, and this is supposed to be a circle here, take a closed loop path around that, that current carrying wire, and do the integral of the magnetic field along that path, and make sure your path is closed. We'll call the path C. That's going to give you the constant magnetic permeability mu zero times the current which pierces through the surface. And the surface here in question is this surface right here. And there's only one current coming through this surface out at us, out of our screens. And it's the current I here, right? The current I. I've drawn a dot means, a dot with a circle around it means coming out of the board, right? So the current enclosed, or the current that pierces through that surface, is I on the right-hand side. And on the left-hand side, the magnetic field is constant at fixed radius. So as soon as we choose lowercase r to be fixed, which is what we've done when we've chosen a circular path, B actually pulls out of the integral. So B dot dl is equal to integral closed of magnitude of B times magnitude of dl. Because dl and B are parallel here, dl points tangent to the curve, and the magnetic field is also tangent to the curve there. They're both in the theta hat direction, technically speaking, and so when we do the dot product, we get magnitude times magnitude, and they're parallel, so there's no angle between them, so there's a cosine 1, a cosine of 0, which is 1. And the magnetic field can pull right out of the integral here. So it's integral of dl, and this is simply the magnitude of B times 2 pi r, the total length of that curve that we're integrating over. And this allows us to equate this side now, so mu 0 I, and this implies that the magnetic field is mu 0 I over 2 pi r. Okay, so that is how you get the magnetic field there. To get the direction there, you understand the direction is going to be parallel to that path, dl, parameterized by dl, and it's going to curl around the current carrying wire according to the right-hand rule. And the vector, if you stick your thumb perpendicular to the xy plane, your fingers curl in the theta hat direction. So you can use that to figure out the direction there. So if I add in there a theta hat, then I get the direction as well. And then we can break the boundary there, and there we go. So we have the direction. To find the magnetic field there in the middle, we understand that at the midpoint, that means that R is going to be 5 centimeters for the wire on the left. Let's maybe call it R1. And R2 here for this wire is also going to be 5 centimeters. So the magnitude of B1 is going to be equal to the magnitude of B2. If I call this one, let's say B1, and this one B2. But they're going to be in opposite directions, because by the right-hand rule, the magnetic field B2 is on the left-hand side of the current, and so it's going downward. And by the right-hand rule, the current on the left has its magnetic field in the middle going up. So equal in magnitude but opposite in direction. That means that the net magnetic field is 0. now I think it's a good time to go and check on the groups again. So that's what I'll do now.
Hello, Professor.
How are we doing in here?
Licks in the bathroom. But we're doing well.
What are we getting here? Are we able to explain our reasoning to each other?
Yeah, we were working on, we got finished with part B and we were starting on C. Our reasoning for A was that since they're opposite directions, it's just they cancel out and it's 0. And then for B,
Explain part A to me in a little bit more detail.
got it. So since the currents are traveling in opposite directions, the magnetic fields are negative of each other.
Hold on.
Inverse.
The currents are traveling in opposite directions.
Are they not? Are they the same direction? Oh, they're traveling in the same direction. They're
Right.
traveling in the same direction. So because of that, the magnetic field between them is 0.
You need to be a little bit more detail. So why is the net magnetic field 0?
Because in the middle, the midpoint, the distance to each wire is the same.
Mhm.
And if you do the right-hand rule, it shows you that the magnetic field is opposite on each wire.
Okay. So you said the distance between the two wires was the same.
And at the midpoint,
What does that imply for the magnitude of the magnetic field?
the magnitude is the same, but opposite.
Right. So because we're equidistant from each of the wires at the midpoint, the magnitude is the same, but the right-hand rule tells us the direction of the magnetic fields are opposite. Okay, good. I'm going to go to the next room. Are you two done? Is that why you've left the room?
Yeah, we all compared answers and we got the same thing, so we came back.
Okay, so maybe you can explain your reasoning for your answers to me right now.
Okay.
Maybe Alberto can start with A, and then maybe Sarah, you can do B.
Okay.
If Alberto is here. Okay, he is.
Yeah, so since the currents are going in the same direction, we figured there would be no magnetic flux in the center.
Magnetic flux?
I'm sorry. Magnetic field would be canceled out
Why would they cancel out?
because they're going in the same direction.
They're going in the same direction?
Yeah, they're both pointing out, aren't they? The current.
Okay, so explain like I'm 5. So give me the full logical reasoning why the magnetic field in the middle is 0.
So the way I looked at it was, if you do the right-hand rule on either side, they would end up getting the same signs just in the center or opposite signs. I don't know. I can't think. So
Take your time.
yeah, so I just figured that they would be curling in the same direction around the thing, canceling it out. So we figured it would be 0. That's how I figured it.
So they would be curling the same, but at the midpoint they would be
Opposite
of each other. So that tells you one aspect that needs to be true for them to cancel. What's the other aspect that needs to be true?
They have to have the same magnitude.
They have to have the same magnitude. So can you explain that part to me?
Well, since they have the same magnitude, then one would be in the negative and the other one would be positive.
How do I know they have the same magnitude?
Because this says 2 long straight carrying wires with 4 amps. So they have the same amps or the current.
But that's
Same magnitude
right.
of current.
Yeah, so that's what I'm saying. So if they have the same current, how do I know they have the same magnetic field?
My brain's broken right now.
No, just take your time, think about it.
Well, they're the same length, right? And that's something we take into factor.
You're not length, but
And they're parallel.
not length, not length. What is the distance that we're interested in for the magnetic field? It's not length.
Distance between the two. But then that doesn't really matter, right?
Not the distance between the two wires, but the distance from where to where?
From either point, from the center point, from left. They have, so they're 5 centimeters from the left.
There you go.
So each one.
Yeah, so it's the distance from the wire to the midpoint, right?
Right.
That is the same for both of the current carrying wires.
Right. Correct.
So why does that imply that the magnitude of the magnetic fields are the same? I'm 5. I don't know how the magnitude depends on the distance from the wire to the midpoint.
So the way I see it is like the left wire is affecting the midpoint in the exact same magnitude as the right wire, but in the opposite direction. So then both will cancel each other out and it'll be 0.
Right, but I still don't understand why the distance matters. Why isn't it 0 everywhere in the middle?
Because otherwise, if you only looked at the distance, let's say it wasn't in the middle and it was slightly closer to the left, then the strength of the current or whatever would affect the point more than the would on the other one.
You mean the magnetic field?
Yes.
Okay, so that's what I'm getting at. So how does the magnetic field depend on the distance from the wire to the point you're interested in?
It's based on both amplitude and, current and the distance from it. But since they're equidistant from each other.
How does it depend on the distance?
I don't know.
So how does the magnetic field, how does it depend on the radial distance, right? If I increase R, does the magnetic field go down or does it go up?
It goes down.
It goes down. How does it go down? If I double the distance, does it go down by a factor of 6, 9, 12?
Oh, I forget. If you double the distance, it goes down by half. Or it just.
It goes down by half. So a 2 in the denominator, is that what you're saying?
Yeah.
Okay. So
it cuts the magnetic field strength in half.
So B is proportional to what?
To the distance.
B is proportional to R?
The distance.
To the inverse of it.
The inverse of the distance.
Inverse. Okay. I don't know if I missed what you said there, but yeah, good. So B depends on 1 over R, right?
Right.
So you have to know that too, right? You have to know how to use Ampere's law to figure out the relationship that the magnetic field has with the current and the distance that you are away from the wire, right?
Mm-hmm.
So in probing your understanding there, I hope that you've pointed out to yourself where your gaps in knowledge are, right? So that way you can address them and be ready, like you're better prepared for the test, right? So I hope you don't see it as me picking on you. I wasn't trying to. But yeah, so now you kind of know maybe where your weaknesses are for that. So address those when you're studying, right? Okay, Sarah, so explain to me part B.
Okay, so first let's talk about the direction.
Okay.
So if you use a right hand rule on either one of the wires, really, because they have the current, both of the currents have the same direction. If you point your thumb out of the page, you curl your fingers around,
Okay.
you can see that the current is going counterclockwise.
Counter
Or
current.
yeah. Oh, sorry. The magnetic field is going.
Oh, magnetic field.
counterclockwise.
Okay. It's going
Yeah, for both of them.
counterclockwise. Okay.
So that means at the point where at the point 25 centimeters to the right of the midpoint, right? That was part B.
Yeah.
Okay.
24 centimeters. Yeah, it's to the right of the midpoint, sure, but yeah, if you did it some other way, like 24 centimeters to the right of the rightmost wire, that's fine too, because it's basically the same problem, right?
Yeah.
Yeah.
Okay. Well, yeah. It would be conceptually, yeah.
Conceptually, it's the same. Yeah.
So that means you would be to the right of both of the wires, and that means the resulting magnetic fields from each of the wires would be going up.
Okay.
So since both of them are going up, you add them together and use the formula for magnetic flux.
Magnetic flux.
Magnetic field.
Magnetic field.
I know.
Okay. So even though I'm 5, I spoke with Alberto. I get the
Right.
sense that magnetic fields are vectors, right? So why would we add the magnitudes of the magnetic fields together?
We add them together because magnetic field vectors are, I think the word is additive.
What I mean is specifically, why would we add the magnitudes? You mentioned the direction was up,
Right.
and then you said we will add the magnetic field magnitudes, I think. So why would we add the magnitudes?
Because because both of the fields are going in the same direction,
Okay.
which I said was up.
Okay. So up, but they're both the same direction.
Yes.
Okay. How would you calculate the magnitude then? So they're 25 centimeters to the right. So what does that mean?
Well, first
You can give me your interpretation of the problem. Remember, it's conceptually the same, but how would you calculate the magnitude?
Right. So first you need to figure out the distance between the point we're dealing with and to each of the wires.
Why do we need to know that?
Because the magnetic field is inversely proportional to that distance for each of the magnetic field.
So if we're 25 centimeters away versus 50 centimeters away, which one is going to be a bigger result?
The field that is 25 centimeters away would have the bigger field, and it would be twice as much.
Okay. All right. Yeah. So how would you calculate your answer? Go ahead and do that part now.
Okay. So you use the formula mu naught times current divided by 2 pi times the distance.
Okay. Where did you get that formula from?
From it's from I know it. Why am I blinking out? It's from hold on. It's from Ampere's law.
Yeah. Right.
Yeah.
It's from Ampere's law. Exactly.
Yeah. And so, like I said earlier, we need to find the distances between the point and each of the wires,
Mhm.
And so for the closer wire, the distance would be the distance would be 20 centimeters. And then for the wire that's farther away, the distance would be 30 centimeters.
Okay, and how come those two distances are different?
Because, like I just said, one wire is closer to the point than the other wire.
Okay.
So that means there's going to be a difference of 10 centimeters between them,
Okay.
which is the distance between the distance we know is between the wires.
Okay. That kind of makes sense because you said 20 centimeters and 30 centimeters.
Yeah.
So you subtracted something from one of them and added something to the other one so that the difference was 10. How did you do that?
Yeah. So I said it was 25 centimeters to the right of the midpoint.
Mhm.
And well, the midpoint of 10 centimeters is 5 centimeters. And if you're 25 centimeters to the right of the midpoint, that means the closer wire is 5 centimeters closer than 25 centimeters. So it becomes 25 minus 5, which is 20 centimeters. So that explains the closer wire. As for the farther away wire, because you're 5 centimeters away from the midpoint, that means you need to take the 25 centimeters and add 5 centimeters to that, which would be 25 plus 5 equals 30 centimeters.
All right, good.
That's how I got the,
Good. Go ahead. What did you say for the numerical?
I was just saying, so that's how I got the 20 centimeters and the 30 centimeters.
So what did you get for the numerical, just for the completeness' sake?
Sorry, I don't understand what you mean by the numerical.
What numerical value did you get for part B?
Oh, for part B?
Yeah.
It got 6.67.
Mm-hmm.
I think it is, it's micro Tesla.
Okay. Yeah, good. So did you guys complete 20? Or sorry, part C, I mean?
Yeah.
Okay. All right, I'm going to go to the next room because I was here quite a while. I'm going to go to room 3 now.
Okay.
Hello. Just got
Hi.
group 2. So I'm probing for understanding now, okay? I'm probing for understanding. So I will ask Alex to explain part A to me, and Tatiana, I will ask you to explain part B to me, okay?
No pressure.
Okay.
No pressure.
Alex, explain
Yes.
explain to me how you approach problem A.
Okay. Well, I'll be honest, I'm still a little confused on that one. I just know about the midpoint. How it'd be 0. But I can't explain it well.
Well, regardless of whether you can, regardless of whether you know the answer to be 0 or whatever, the important part is that you understand it, right? So we're going to walk through what you do understand and hopefully arrive at the correct understanding. So start from something you know.
Okay, I know you have to use Ampere's law.
You know to use Ampere's law. Okay.
Yeah.
What is Ampere's law? How does that apply to this problem?
Well, you're given the current and the distance. So you can use that.
Distance in what sense?
Like how far away they are. Like
How far away you are from what?
The 2 wires.
The 2 wires at the same time, or how far away you are from one wire and then how far away you are from the other wire?
How far away they are from each other, and then knowing that you know the midpoints.
Okay.
it just be half of it.
So you've identified the midpoint.
Yeah.
That's what you're saying. Okay. So so now, how do you apply Ampere's law with that information? What goes into Ampere's law?
The what do you call it? The current, which would be 4 amps, and the distance, which would be wait.
Take your time, no pressure.
Because the R is the radius. Right.
R is the radius. R is the radius of what, though?
The wire,
The radius of the wire?
or like from the wire, like the distance
The distance from the wire to where?
to the midpoint.
Is the midpoint, could be any point though, right? But we're specifically interested in the midpoint?
Yeah, because that's what it's asking for the midpoint.
Right, so it's asking us about the midpoint specifically, but it could be the distance from where again?
From the point, the first point to the second point, the distance.
Wait a minute, so now you've changed what you're saying. So from the first point to the second point, what do you mean?
The 2 wires. I mean,
But we don't, are you saying you're using Ampere's law to treat both wires at the same time? Is that what you're saying?
I got a little mixed up.
How do we use Ampere's law? Yeah, Tatiana, hold on to your thoughts a little bit. Hold on to those thoughts. We want to let Alex give it a good thinking and really try to probe where the misunderstanding is, so that way we can address that specifically. So, Alex,
Yes.
the first time you said, when you use Ampere's law, that the distance is from the wire to the point that you're interested in.
Yes.
Then you said it's from one wire to the next wire. Which one should we use for the distance?
From one of the points to the midpoint.
One of the points to the other point? That's very ambiguous.
To the midpoint. Sorry.
One of the points to the midpoint, what does that mean?
Will it just be, well, I guess for Ampere's law, you'd have to use it like for each wire, like the distance for each one.
The distance for each wire, what does that mean?
Like the leftmost wire to the midpoint, and the midpoint to the rightmost wire.
Stop right there. Stop right there. We need to refine what you're saying, because what you're sometimes you're changing what you're saying, and you're changing the meaning of what you're saying. So you need to say, this is the proper way to say it, because I think at this point I feel like I should tell you how to say it properly, so there's better communication. So you want to say the distance from the wire to the point you're interested in knowing the magnetic field. Let me type that in chat for you, so that way you can kind of read it and really see what's meant there. So the distance from the wire, and actually it's the center of the wire, to the point you want to know the magnetic field at. Like that, okay? Can you just read that out loud for me one time?
Yeah. The distance from the center of the wire to the point you want to know the magnetic field at.
Right. So in Ampere's law, you have like an integral, right,
Mhm.
of some closed path. What closed path are you going to choose here?
You mean like the distance, like path?
Yeah, so you have, when you do Ampere's law, it says to take an integral of the magnetic field over a closed path, right? What kind of
Yeah.
closed path are you going to use?
The distance from the center of the wire to the point.
Distance from the center of the wire to the point is
You
not a
know,
path.
okay.
What path are you going to use?
I'm a little confused on what you mean by path.
Okay, so in order to execute Ampere's law, which we agree we have to use Ampere's law if we want to know the magnetic field, right?
Yes.
So in order to execute Ampere's law, you have to do an integral of the magnetic field along some path. And that path, if you look at my camera, that path could be any path that closes upon itself, right? So it could be some rectangular path like this. That would be okay. It could be like some kind of crazy squiggly path that comes back to where you started, right? But what's a natural path that you might want to choose if you had a long straight wire like this? Do you have an idea?
Just Would it be like a straight line, kind of?
Would a straight line be a closed path?
No, like a cylinder. Wait.
Cylinder? I like cylinder more than I like a straight line. Because a cylinder, I can see a cylinder is kind of like a closed shape, right? So that makes more sense, right? What kind of symmetry do we have here for these wires? Do we have cylindrical symmetry?
I think so. They're just like in a straight line.
Yeah, because there are straight lines coming out at us, right?
Yeah.
So I could imagine, maybe you could imagine too, right? You could imagine like this pen here, there's like a cylinder around the pen, right?
Yeah.
So what kind of path would be cylindrically symmetric that we could put around this wire? In other words, like, what's a one-dimensional cylinder?
A circle.
A circle, right? If I were to draw a circle around the current, that would be a closed path. Then I could apply Ampere's law, right?
Yeah.
So what does Ampere's law say in words? Can you describe what it says in words to me?
Ampere's law in words. Ampere's law would be the line integral would be around the closed path.
Is that it?
That's all I can think of, really.
That's not Ampere's law, though. Ampere's law is a statement about that integral. What does it equal?
The current times the
Some constant, right? It's just some constant times the current. Is it any old current? Like, for example, if I drew a closed loop around the left wire, if I drew a closed loop around the left wire, would the current of the right wire affect my calculations?
No, because it'd be closed. The path.
Well, I could draw a closed path around both wires, right? That would be
Yeah.
closed still.
Oh, well, then that would affect it since it's within it.
It would affect
Right.
what? Say that again?
Then it would affect the magnetic field since like, whatever's inside the closed path.
So, okay, say that one more time. Whatever's inside the closed path. Say that part again.
Whatever is inside the closed path will affect the magnetic field.
There we go. Exactly. So only the current inside the closed path, and really it's the current that kind of penetrates through the surface that is enclosed by that closed path, right? Counts towards Ampere's law. It's the I enclosed. It's not any I, it's only the I enclosed that goes through that path, right?
Yeah.
Okay, so in words, again, one more time, explain Ampere's law to me.
Ampere's law is the current enclosed in an enclosed path times the constant, which is equal to which affects the magnetic field.
Be more specific.
In an enclosed path.
Not just the magnetic field in the closed path, but the start from the left-hand side of Ampere's law and then go to the right-hand side.
Okay. So the line integral of the magnetic field around the closed path is equal to the current enclosed times a constant.
Right. What's the name? What's that constant called? Do you
Mu?
know?
Mu?
Mu. Right. So mu naught, right? Mu naught
Yeah.
or mu zero. Right. So exactly. So it's some constant. So the line integral around a closed path of the magnetic field is proportional to the current through the surface, which has a boundary that is the closed path, right? That's a little bit more technical than we need really for a conceptual understanding here, but that's good. So we're starting to identify little misunderstandings, right? And we're kind of addressing them one by one. So I hope this is helping. I'm not really trying to pick on you. I'm just trying to get you up to speed, right?
Yeah.
So now that you've identified we need to use Ampere's law, you've identified how to use Ampere's law. Now, can we use Ampere's law for both of these wires individually?
Yes.
Okay, so you now continue the explanation. So you're explaining how to solve part A now.
Okay, so you use Ampere's law for both sides of the wire, like the leftmost side to the midpoint to the rightmost side.
Uh-huh.
And then since they are opposite in direction, they cancel out. And because they're the same distance away as well.
Okay, so why are they opposite direction?
Because, well, it's from left to, wait.
So I don't know. Did you say something there?
No.
So why are they opposite in direction?
I'm not sure exactly why.
You say that they
Okay,
produce
hold on, Tatiana, hold on. We don't want to rob him of his opportunity to learn here. Okay, Alex, how do I find the direction of a magnetic field?
Use the right hand rule.
Right hand rule, so you know how to find the direction.
Yeah.
So is it possible, could we find the magnetic field of one wire and then maybe find the magnetic field of the second wire?
Yeah.
Right?
And then once you find it for both, you'll notice that they cancel. And then.
So you're saying we can just add those together, right?
Yeah.
Okay, and you found the direction of the vectors to be opposite, right?
Yeah.
using the right hand rule. Explain to me how you would use the right hand rule.
Okay, so the right hand rule, like you place use your right hand.
Okay,
And
here's my
then-
right hand.
Yeah. And then you want to wrap your fingers around the current
So like how? What do you mean by that?
in the direction it goes.
Wrap my fingers around the direction the current goes in? So
And
like
then-
this, or you have to be very specific. So take your time and think about it.
Yeah. Or actually, you wrap your hands around the direction of the magnetic field.
That's what I'm
And
trying
then-
to figure out, though, isn't it? So how do I do that if I don't know the direction?
Your thumb should be pointing in the direction of the current.
Ah, that's what I was looking for, right? So without that, I don't know how to, I mean, I can just wrap my hand in any number of ways, right? So
Yeah.
you've got to remember, okay, thumb in the direction of the current. Now it's clear, right? If I have my thumb in the direction of the current, now I can see that for that current on the left, the magnetic field is going to go up, right?
Yeah.
Okay. And then by the same logic, thumb in the direction of the current for the second wire, the magnetic field is going which way?
Should be
Down.
going down. Yeah.
Right. Good. So for the right hand rule, explain it to me one more time.
You want to get your thumb to be in the direction of the current, and
Uh-huh.
then you wrap your finger around the direction of the magnetic field, and that would show
Okay.
you.
Let me correct you slightly there. You said thumb in the direction of the current. Good. Then you said wrap your fingers in the direction of the magnetic field. We don't know the direction of the magnetic field. So you should say put your thumb in the direction of the current and your fingers will curl in the direction of the magnetic field.
Yeah, because that's how you
Then-
find it.
Then it's unambiguous, right? Because your fingers are curling in this direction, right? So, oh yeah, okay, they're curling in that direction. That means that's the direction of the magnetic field.
Got it.
Okay, so we've identified that the magnetic field of one wire and the other wire are in opposite directions, but that's not enough, is it?
No, because the magnitude.
Exactly. So explain to me what's going on with the magnitude now.
Okay, so since the midpoint from the leftmost wire to the midpoint,
Mhm.
or let's say the total distance between the two wires is 10 centimeters.
Mhm.
So the middle of that would be 5 centimeters.
Mhm.
And that'd be the same for both sides since it's the midpoint.
Right.
So the magnitudes would be the same.
Okay, see, there's a gap there. How do we know the magnitudes would be the same just because those distances are the same?
Because magnitude is, it doesn't matter like the sign. Does that make sense? Like it could be positive or negative, is its magnitude. Is the absolute value of it.
But that's not necessarily the question that I'm asking. That doesn't answer the question I'm asking. So, how do I even know that the magnitude of the magnetic field even depends on distance?
You would use Ampere's law.
And how does Ampere's law tell me the magnitude of the magnetic field depends on distance?
It's related to 1/r. That would be,
Related to, instead of related to, do you mean like proportional to?
proportional, yeah.
Okay, good. So that's better mathematical language. Like is proportional to, it makes a lot of sense.
Yeah.
Okay. Is that all that it's going to depend on? It's going to depend on just 1 over the distance. What else does it depend on?
Also the current, but the current would be the same. It'd be 4
Oh, okay.
amps.
How does it depend on the current?
It's proportional to I.
It's
To the current.
proportional. Oh,
Yeah,
okay.
proportional.
So it's proportional to the current, and it's proportional to 1 over the distance. Is that what you're saying?
Yeah,
Okay, and is there some sort of constant there as well?
yeah. It's
What's the
also
constant?
proportional to mu naught.
No, no, just tell me what the constant of proportionality is.
Like the value of mu naught.
Yeah, so it's proportional to I over R, is what you've said, right?
Yeah,
What is the constant that we multiply to make it equals?
mu naught over 2 pi.
There you go. Exactly. Good. So we've established using Ampere's law the magnitude of the magnetic field. We've established the direction of the magnetic field with the right-hand rule. And now we can combine all of that. So now give me the explanation why the magnetic field is 0 in the middle.
Okay, so I'll start with the direction. Okay, so we have to find the midpoint. So the midpoint between the 2 points will be in the middle. So 10 centimeters, I mean 5 centimeters in the middle. And to find the direction, you have to use the right hand rule,
Mm-hmm.
and your thumb will be pointing in the direction of the current.
Mm-hmm.
And then whatever it's pointing at, your hands will naturally wrap around the direction of the magnetic field.
Okay.
And then you do that for both sides, and you will notice that the magnetic field for the leftmost one is up, and then the rightmost one is down.
Mm-hmm.
So you notice that if they were to be their magnitudes to be the same, they would cancel out. And then
Mm-hmm.
you have to find the magnitudes, and then to find the magnitudes, you use Ampere's law,
Mm-hmm.
which is the magnetic field is equal or is proportional to the current over the radius times the constant. And then the currents are the same, which would be 4 amps, and the radius would also be the same.
Okay.
Since it's the midpoint.
Perfect. You see how we went from barely any understanding to like a complete understanding?
Yeah.
That's what you need to do for every problem. And it gets easier and easier the more you know, right? So you've now gone from very little understanding to very good understanding in, not that much time,
Yeah.
just talking through it, right? So that's very good. Now, Tatiana, you've had a lot of time to think and listen, so you'll probably explain part B to me pretty good. So let's hear it.
So this is all hypothesis, but what I'm thinking is you combine left wire to the right plus. So Q naught I over 2 pi times sorry, hold on, I didn't write it down. Okay, yeah, I'm back. All right, so you add magnetic field from the left to the right wire. So since the total distance from left to right is 10 centimeters, and we're looking at 25 centimeters to the right, we're adding 5 centimeters to the 25 for the distance, because we're looking at the total first. Because so the way I drew it is basically split it in half, going from the midpoint, and then you add it to the difference, which is 20 minus 5 from middle to 25, yeah. And then so
let me pause you right there for a second. So your strategy here is to first identify how far away that point of interest is from the 2 wires individually. Is that correct?
yeah, seems
Okay.
like that. I mean,
No,
there's,
go
I know
ahead
there's
and-
a faster way.
No,
The
that's
faster
fine.
way, since we have the constant. I mean, let me just talk through it again. Since we have now the constants mu naught I over 2 pi, right? So we just multiply 1 over 0.30 plus 1. Did I say 120?
Let's not focus on numbers just yet, right? Numbers are not understanding. Numbers are calculation. So let's continue with how we solve the problem with the reasoning first.
Okay.
So
So like you
you've
said-
explained to me how to figure out the distance from the wire to the point.
Mhm.
What else, what else do we need to know?
Well, we already know that both wires have are going to the same direction.
How do we know that?
Let's say magnitude direction of the same direction from the problem. So the
Oh,
current
for the
in
currents?
the,
For the currents?
yeah,
Oh, okay. Yeah, that's given to us. So what does that mean? We're trying to calculate
adding-
magnetic field, right?
right. So the total magnetic field, we basically have to combine both magnetic fields from the left to the right.
How do we combine the magnetic fields?
You calculate magnetic field of the right wire first or left wire first. Well, it doesn't matter which one. And then calculate magnetic field of the right.
What does that mean though, that word? What do you mean by combine?
Add.
Add them. There we go. Okay. How do we add them?
I mean, magnetic field from the left plus magnetic field of the right. Is that what you're asking?
Yeah, very close. My question is more oriented towards the vector nature of the magnetic field, though. So how would we add them if I knew the magnetic field at one point? Let's say I knew its magnitude. Like, could I just add magnitude plus magnitude? Is that okay? Or
Sure. Magnitude, as long as you know the direction of the magnitude.
as long as you know the direction, do we know the direction in this case?
Yes, we're going to the right.
We're going to the right? What do you mean?
Problem is asking is that we're
Can you say
we
that
go
again?
back. Because you're looking for the magnetic direction to the right.
Right. What's the direction of the magnetic field to the right of wire 2?
Down. This is the opposite.
How would we find the direction?
Right hand rule.
Right hand rule. So how do I apply the right hand rule in this particular problem? So how do I apply the right hand rule?
Magnetically makes sense.
Can I just point something out really quickly? I find it really interesting. Alex didn't know how to apply the right hand rule, or at least explain how to apply it at first. Then we took him all the way to being able to explain how to use it. And I think I think before that you had a sense of how to apply it. And now you somehow like don't know how to apply it in this situation. I find that kind of interesting. but we're going to make sure that you know how to apply it by the end of this for sure. So, I mean, so we got to use our right hand first. So maybe we can figure it out if we just use our right hands. So try get your right hand out and try and play around with it. And what is the correct process there for finding the direction? So Tatiana, do you feel like you're making progress thinking about it on your own, or should I explain at this point?
I mean, I'm seeing, I'm visualizing it's going upward, but I'm kind of, I'm having a little bit of anxiety right now.
Let me try to fill in the gaps, right? So there's, you know, sometimes you have to learn from somebody who knows, right? So what I went through with Alex was, at first he was kind of telling me wrap my fingers in the direction of B, right? But that kind of assumes the direction already. What you want to do is put your thumb in the direction of the current, and then your fingers will tell you the direction of the magnetic field. So from your perspective, out of the page, right? This is my right hand, by the way. So if this is my right hand, make sure you're using your right hand. For me, on the left side of the wires, it's going down. It should be the same for you as well. And on the right side of the wires, it should be going up. So my fingers curl in the direction of the magnetic field. My thumb, I stick it in the direction of the current, which is out of the page. So do you have your right hand up? Can you do that?
Yeah.
Okay.
Oh, I was turning it the other way. Instead of out of page, I was doing parallel. That's what I was doing.
Yeah. See, that's a common issue I see with students is they get the sense that, oh yeah, right hand rule, but then they only apply it correctly in some cases. There's maybe 2 or 3 versions of the right hand rule. And so you want to be able to apply the best one for your situation. So for this situation, thumb out of the page, fingers are telling you the direction of the magnetic field. So the magnetic field is curling around the wire counterclockwise. Does that make sense? Did that make sense, or?
Yes.
Okay. Could you explain it back to me now?
Okay. Since we're curling our right hand around the wire that's going out the page. In our case, our fingers are curled upward or curling upward. This instance.
Good. So since our fingers are curling upward, that means what?
It's positive.
No. What is that? What does that tell us? What does the fingers going up tell us?
The magnetic direction of the magnetic field.
There you go. Direction of the magnetic field, exactly. Sometimes it's very hard to kind of figure stuff out when you're not using the right language, right? So it's very important to make sure that you nail down the right language when you're talking about stuff, because if you allow your language to kind of shift and change over time and you don't really have a concrete way of communicating certain things, that's when there starts to be like little things kind of creeping in and messing you up sometimes, right? So it's important. Fingers in the thumb in the direction of the current, and your fingers will wrap around or curl in the direction of the magnetic field. So when my fingers point up over here, that tells me that the direction of the magnetic field is up at that location. Does that make sense?
Yes, sir.
You want to explain it one more time?
Okay. All right. So when we're on this problem, when we're looking at the direction of the magnetic field, we mentally wrap our fingers around a wire, pseudo wire, so to speak. And since going outward from the page or from the screen or whatever, the wires coming out, our fingers are curled upward. That's pointing to upward magnetic field.
So what does that mean about the magnetic field?
That's going out.
There you go. Right. That's the part you keep forgetting on the end there. So your fingers are curling up. That tells you the direction of the magnetic field. Good?
Yes.
Okay, so we've established how to get the direction of the magnetic field 25 centimeters to the right of the midpoint. Now, to recap, what you've said is that your fingers point up
Right.
after applying the right hand rule for each of the wires,
That is correct.
which means
Magnetic field goes up.
goes up. And so if both the magnetic fields go up, then
Excuse me.
say that one more time.
You add them since they're both going in the same direction.
There you go. Yeah, so they're both pointing in the same direction. That means you can add their magnitudes, right? So when two vectors have the exact same direction, it's okay to add their magnitudes. But if they didn't have the same direction, it wouldn't be okay to add their magnitudes, right?
Right.
So walk me through the final steps of the problem here. So how do we get the magnitudes?
So since they're going the magnitude goes the same direction, or magnetic field is in the same direction for left and right wire, we just add them together.
Add them together, but I don't even know the magnitude of one wire.
Well,
How do I
you
get
not
that?
since the total distance, you split it in half.
We already know, so you've already explained the distance part, right? You've already told me 30 centimeters and 20 centimeters. We got that. How do I find the magnitude of the magnetic field, though? Is there some sort of rule, like right hand rule or something, maybe that I apply in these types of problems, or?
Isn't that what we're talking about?
Yeah, we already did right hand rule, right? But what's the right hand, like what is there a rule of thumb or something that we can use to calculate the magnetic field?
Not thinking. Hold on. I'm not thinking. So we know that we're going to the same direction. And we know that to get the magnetic field, we have to add. I don't understand what you're asking, I'm sorry.
How would I calculate the magnitude of the magnetic field if I didn't know anything about a formula or, I don't care about the formula. I care about the understanding, right? So the formula can be reproduced if you have the understanding, right? If you understand how to get the magnetic field, that's better than knowing the formula, right? So what law can we apply in situations like this? Is there a law that we can apply for situations like this?
Gosh, keep thinking Maxwell, but that's not right.
Not quite Maxwell, but you're close though. Is there a law that's kind of similar to Gauss's law that we can use symmetry to kind of figure out the magnetic field in a little bit of an easier way than perhaps using Biot-Savart? If you even remember Biot-Savart. That one's kind of the worst one. Do you remember the four Maxwell's equations?
Oh, you want equations?
Like just their names? Like you don't have to remember like the exact equations, but do you remember their names? So
No.
so there's four of them, right? You know there's four of them?
Okay. Sorry.
It's
My
okay.
mind's already gone because I'm thinking I'm all over the place because I'm going to Ampere's law and columns.
So Ampere's law, I like Ampere's law. Let's investigate Ampere's law. Let's see if Ampere's law is correct or not. Right? No, there's no problem being wrong. If we try something and it's wrong, we'll know, and then we know what not to do, right? So let's test Ampere's law. So explain to me, what is Ampere's law? Just give me kind of like a general idea of what Ampere's law is. It doesn't have to be perfect. We can probe, we can improve our understanding through
Is it
questioning.
mu naught 2I or mu naught I? Is that the one?
Mu naught I, okay. I think that sounds familiar, yeah. Is there something else there? So mu naught I, what's on the other side of the equation?
Closed magnetic field.
Magnetic field, okay. That kind of makes sense.
DL, I think.
EL, okay. So if I have a differential, do I integrate or
Oh,
say it again?
closed thing. Closed integral.
closed integral. Okay. Closed integral over what? What's closed?
I need to check that out. So it was, the formula was like closed integral b times dl. I think that was.
Right, right. And what is the dl for? What am I integrating? Like, what is closed, right? Is it like a closed surface?
Surface.
Is it a closed surface?
I think so.
What do we use? What do we use for our differential when we're talking about a surface? Do we use dl? Do we use dx? Do we use dv? Do we use dA? Do we use ds? What do we use?
dA.
dA, right? We don't use dl for a surface. What do we use dl for? What else can be closed besides a surface?
Sphere. No.
A sphere is a surface, so that's closed for sure.
I had that earlier, just not.
What about, maybe I'll give you a hint. What about like a circle? Would a circle be closed?
Yes.
If I went around a circle, what would I call that? What if it was like a potato shape instead? Like it's not a perfect circle, but it's like a potato shape. Is there a name that we have for something like
No, I
that?
know what you're saying. I know what you're talking about. I just don't remember the name of it.
Okay, so we usually call that a closed path, right? Or a closed loop,
Thank you.
right?
Look, there you go. Thank you.
Yeah. Okay, so closed path or closed loop, or you could even say a closed contour. That's kind of like older language. So we have, remind me again, a closed integral over
B times dl.
b time. So b, not b times, right? It's not b times dl, is it?
B dl. I just the way I remember it. B dl.
But b is a vector and dl is a vector, right?
Right. So B is Q naught, mu naught over 2.
We haven't proven that. We haven't proven that. We're not there yet. So what is b? Is b just a scalar? Like you just multiply things by b, or is b a vector?
It's a vector.
It's a vector, right? dl is also a vector. How do we multiply two vectors? Is there a way to multiply two vectors?
Give me a hint because I'm
Okay,
thinking.
dot product.
Oh, yeah,
Dot product, right? We've seen that a lot. It's b dot dl, not b times dl, right? I know it seems kind of like a small distinction, but it's really important because it means x component times x component plus y component times y component plus z component times z component, right? So it's more than just a multiplication. It's a specific kind of multiplication and a summation, right? So b dot product with dl, and we're integrating over a closed what is it called again?
Loop.
Loop, exactly. So it's closed loop. And when we integrate B dot dl over a closed loop, what does that equal?
That's a mu naught I.
U naught I. And is it any current or is it a specific current? Can I just plug any current I want into that formula? Like I have currents all over the place and I just take them all and I plug them into the formula?
It's the applicable current now.
Say it one more time.
It's the applicable current, whatever you're looking for specifically at that point. Or
The applicable current. I don't agree with the language there, but let's try and refine the language. So if I were to draw a loop and I had some currents inside of my loop and some currents outside of my loop, which ones would I plug in for I? Would I plug the currents in the loop or out of the loop?
within the loop.
Within the loop, right? So it's the current in the loop that goes on the right-hand side of Ampere's law. Does that make sense?
Yeah. It
So
does make sense, but it won't make in 5 hours.
well, when you probe like this and you really kind of start questioning things, that's when students really start to remember, because they start to remember the questions they were asked and how to get the answer. And then that process is easier to repeat than it is to just blindly memorize something. So hopefully not in 5, hopefully you sleep on it and actually remember.
I mean, I have to get up in 5 hours.
You have what?
Get up in 5 hours.
You have to get up in 5 hours? You should go then. I don't want to keep you for much longer then. I got like 5 hours or less last night and I feel like crap. So yeah, just go ahead, but just work on it. You know, you've identified some areas where you're a little bit weak. Like if you can't explain it to somebody, then that's an area of weakness for you, right?
I mean, some things make sense in my head. Just
Mhm.
I don't usually have problem explaining.
Yeah. You got to be able to articulate that, because articulating that in words is just as good as articulating that on the paper. Being able to think about it and put it into words to explain it to somebody is just as good as being able to take it from brain to paper, right? And write the equations down and prove, yes, indeed, this is the correct formula, right? So I don't want to keep you much longer. So you can just leave the meeting, go get some rest. Okay.
But was I on the right track for the solution?
Oh
That's it?
yeah, you're on the right track. It's just that, remember, it's not about the solution, right? It's about the reasoning to get to the solution. Once you get that, then that's when a question you've never seen before is asked to you and you're able to apply the same reasoning, right? If you know what to do for a particular kind of question, you can kind of shortcut your way to the answer. That shortcut method doesn't work for another question you've never seen before. But the reasoning to get the answer for this question is going to work for this other question you've never seen before. You have to apply the reasoning, the problem solving strategy, right? The corner cutting will work over here, but it won't work over here. The problem solving strategy, logic, and reasoning will work in both cases. Make sense?
Yeah.
Okay, go ahead, go get some rest. It's important to have rest. Like it'll help you remember stuff if you can get some good rest. So I don't want to keep you anymore. And I'm going to end this breakout room now and go back with the rest of the class if they're even waiting. They may have already left. So here we go. Close all the rooms.
Yes, we were the last ones.
Everybody's already left, so that's fine. I mean, it was a long time that I kind of went through and was probing everyone, so that's good. I hope people got a lot out of it. I recorded all of this discussion, including the talks with the students, so go back and watch the video if you really want to see the discussions I had with other students. I actually had a discussion with David that wasn't as in depth as with you and Alex and Sarah and I forgot who the other one was, but I forgot the order I did things. But yeah, I think it was Alberto. And Lick was in the bathroom or something. So yeah. Anyways, that's where we're calling it now. Class dismissed. Class over.